Test. Very loud. Welcome, everybody. Yay. A lot of people here. That's nice. Welcome to this year's Onward 2024. I counted. Dick, I think it started in 2002. Maybe this could be the 23rd Onward this year. And yes, Jonathan and I try to manage the whole submission process, overseeing the reviews, and I think we have a nice program which we start today. And first of all, let me thank again, or let us thank again, the entire program committee. So you put in a lot of effort to go through all the papers and all the essays, and found really helpful comments, and a lot of papers and essays were put into shape with your help. So thanks again at this time. We had 30 submissions for the papers and 18 essays, which is a lot, just looking at the previous years. So yes, we reached out to people, encouraged them, hey, do you want to submit? Do you have an idea? Try, come to Onward, we are nice. And after almost 150 reviews, we decided on 11 papers and 11 essays. And we will interleaving those, starting with papers today, then the session on essays, then we have a mixed session this afternoon, evening, where we have 2 papers and an essay, and so on. We will try to keep things fresh here. And yes, and I had to relearn about diameters and areas, because my first attempt was like, no, this doesn't look right. And because the 11 is like 6 centimeters diameter, and the other was like, okay, no, this is not right. And then I discovered pi, and then it worked out. Yeah, that's fine. And I remembered that people can fill out the entire circle by themselves. This is another interesting illusion you can use for these things. So, I just took the abstracts from all the papers and all the essays, and this is what we're looking into. So it's a lot about programming and languages and systems. I see some data in there, configuration, debuggers, interfaces, stack. Oh, there are problems. There's natural language at the bottom, which is really interesting. For the essays, we see general purpose at the bottom. So also the essays, a lot about programming, languages, something natural. There's design in there. We had systems in the papers, a lot of research, something visual. And I think this will be fun, very interesting. Looking forward to your talks. And as you may have noticed, the proceedings are already out. And during the conference, you can also download the ones that are not open access. So I encourage you all to do so now during the days. And then you can have a look at them before the talks, after the talks, and engage in conversations with the speakers. We use Discord for the virtual portion of this conference. So virtual attendees will write their questions in the Discord channel. So we have 2 channels, Splash Onward Papers and Splash Onward Essays. And there's also the presenter announcement channel, which many of you speakers already figured out, where you can ask questions about where should I be, at which time. There's a presenter form to leave some more information about the event. And there you can ask questions before, during, or after the talks, even the on-site people, right? So you can use Discord to get a question off your chest, and even if you don't see the speaker around the halls at this time. All the talks are streamed via YouTube, not Discord, and we are in the virtual Pacific room on YouTube. I haven't checked that, but I suppose it's, yeah. And I put the Wi-Fi credentials for you here as well. They're also at the registration desk. Maybe some last advice. I think you should already kind of know that, but I tried here the 16:9 ratio fits best for the presentation screen, so that the people in the back have most of the text in the slides, and which means both the slide ratio and the laptop resolution ratio you're putting out through the cable. And so for papers, you see from the schedule, we're aiming for 25 minutes, including the discussion. So the longer you talk, the less discussion there will be. Maybe talk about 15 minutes, have 10 minutes discussion, use some slides as backup if you see the discussion can be helpful there. For the essays, we have a little bit more time, which is common for Onward essays. So we plan for 40 minutes, including discussions. So maybe leave 15 minutes for discussion in your talk about the essays. Same principle. And after your talk, please hang around in the session to engage in further discussions or meet again at the coffee break. So that's it from our side. And I think we get started with the first batch of papers.
Thanks, Marcel. It was a pleasure working with you, organizing this. Everything happened pretty efficiently. I also want to add that tomorrow morning at 9, there's a keynote by Richard Gabriel, who is the Onward keynote speaker here, and I strongly advise you to all to go see that. So Oscar Neerstrass is our first author. His paper is called Moldable Exceptions, working in the glamorous toolkit, which is a small talk.
Check? Yeah. Oh, yeah, fine. So, what the? I don't know what that means. I tried different browsers, different devices, same thing. Okay, I don't know what that is. Okay, I'm Oscar. I work for Fink. We're a little company in Switzerland, and we modernize legacy systems by opening them up using what we call moldable development. And the idea is that we want to expose the internal domain models so that they become explainable. So you can really talk to the system live and answer your questions as a developer. And one of the things that we discovered recently is that we can apply this to debuggers as well. So that's what I want to talk about today. Oh, and I should say, I'm only the guy who wrote the paper. I mean, the work is basically Andre's, and he said what we should say. And I'm more of a user. I didn't build it, but I think moldable exceptions are amazing. And Tudor and Andre are really the brains here. So what's the problem with generic debuggers? Well, I don't know what this code, I don't know what a snaffle is or a foo or a bar, I just don't know. But if I run this code, if this code is somewhere and I run it, I get some kind of assertion failure. And I get into this debugger, and the debugger looks like pretty much like any debugger you've seen. You've got this stack, and you can look at the stack frames and so on and say, okay, I failed here. Luckily, the actual problem is at the top of the stack in the present, not in the past, so I'm lucky here. But what the heck is going on here? I don't know. So there's an assertion that fails. I can inspect this guy. Okay, that's a bunch of text. And this is a bunch of text too. But why did it fail? I have no idea. I can maybe open up a code bubble and see what's going on in here and really see. I just see these strings here. So I don't know what's going on. So the debugger isn't really helping me much figure out what's going on here. Well, I mean, one of the things you say, well, that's an assert, and the assertion is an equality, so maybe I should use assert equals. That would be better. And actually, we can leverage this because we know something about what's going on. In the domain, we know that when there's an equality failure, there's something interesting going on here. And we can see that here. Let's dive in. And now we get something a little bit more interesting. I mean, usually when you have an assert equals failing, you'll get a little bit of an explanation. This was not equal to that. But here we can actually see, well, where are the differences? Now we understand something. So we're in a particular context. In the program, we get an assertion failure, and we know that we have some knowledge about what's wrong. So why not communicate that to the developer instead of plunking the developer into a completely generic view that it's relatively useless? Okay, that's one example. Here's another. Here's some code that we want to create a file reference and create a directory, and that's failing too. Directory does not exist. And, well, now we get some more useful information. It's showing us where exactly the failure has occurred, and it's even offering us a choice of something to do to fix the problem. Isn't that cool? The regular debugger view is still there. We get the stack view if we want it any time. We can flip back and forth. And so we have, on the one hand, we can get more information, we get multiple views associated with our exceptions, and we can get fixes which are intelligent. Here's another one. I'm trying to access Gmail from Glamorous Toolkit, our platform, and this also fails. And in this case, I'm plunked into the regular debugger. I can also switch to a view which is showing us which are the redirects that have appeared along the way, but I'm also getting a retry button in both of these views, so I can try and increase that. For example, let's try 6 redirects, and let's go for that, and we continue from the debugger and we actually get to our final result. So that was pretty cool. So what's going on here? So this is an example of moldable development. And the idea is that instead of having an environment with a bunch of fixed generic tools, IDE tools or analysis tools, what we want is we want to take our software system, whatever it be, and augment it with custom analysis tools that answer questions about how it's working and make it explainable. In order to make that work, we need the tools of the environment to be moldable. That is, they're open so that when they see when the tool of our environment sees objects or entities or artifacts coming from our application that are bringing these custom tools with them, instead of just showing the generic tools, it can slot in these custom tools. That's it. The main tool where we spend most of our time molding things is the object inspector. Now think about that. The object inspector is something you normally only see if you happen to get dumped into a debugger and then have the courage to actually start exploring something. Most people, when a debugger opens up, they say, oh, debugger, kill it, close it, and start staring at source code. One of the mantras that I like very much is, the debugger is your friend. So the debugger is trying to tell you something, but it can actually tell you more. Right, so the object inspector is something you normally don't see. Instead, we've made it a central part of an environment. We always want the object inspector, but we don't just want the generic view. We want something a little bit more intelligent. So here, for example, I'm inspecting an instance of this children's game, the Ludo game. And if I were inspecting this normally, you would see something like that. I'm sure you all recognize it. This is one of the worst ways possible to inspect an object. It's like the default view is I can find stuff, but I really have to navigate in an unpleasant way. So why not just tell the inspector, hey, I'd like to see this view. This view is a view of the game that I can actually interact with. I can play the game, or I can open up a little playground, so it's a contextual playground, like a REPL, but it's bound to the context of the object. So I can actually send messages to the object from the playground. I can go to another view and see all the players and start exploring them, and this will take me further on. And notice that I can navigate in a much more pleasant way than with an ordinary tree view. What's kind of cool is I even have a moves view, which allows me to step through and see what the moves of the game were in the past. So I get a kind of a back-in-time debugger for the game for free. What are these things? Well, you say custom tools for every possible question. Oh, that's going to be so expensive. Nobody's going to do that. Well, a fundamental principle is that these tools should be cheap. So all it is a method that you add to your domain object, and you add a little pragma. In this case, it's called GTView. It's like an annotation in Java that says, hey, this is a view. So when the tool sees it, it'll slot it in. Just like when you say a method is a test, then the test runner will see it and say, oh, I recognize this is a test. It's the same principle. And all we have is a very tiny little internal DSL for building, in this case, a columned list with the title, which is moves, and a bunch of columns, and the objects that we're going to list are the moves of the game. So it's a super simple, tiny little DSL. On average, views take about 12 lines of code. So we have thousands of views in Clamor's toolkit itself, and they're all pretty small. Some are obviously much bigger. For example, if I look at the board game, it's an explicit view, and it's going to be reusing code that I actually have a little GUI built up for the game. So that's more work, but it gets reused all over the place, so it's really heavily leveraged. Okay, so we have these views for the inspector. We'd like to have a similar idea, essentially the same idea, and we apply it to the debugger. So here's a Ludo recording game examples. So here I have an example of a Ludo game, which I can instantiate. That's this guy here. So there's an instance. This is just an example. It's just basically a test that returns an object. And if we evaluate this guy, I'm going to get an assertion failure. Why is that? So now I've got moldable exceptions here. If I didn't have the moldable exceptions, I'd be dumped in here with the classical stack view. Instead, I'm going to reuse the views that I had before, and I see, oh, token B does not belong to the current player C. And I can see that now, and I can actually walk through the moves as well and see those. So I get a much better explanation in context of why I got this error and what I should do about it. Right, so the specification, if I look here, I can actually inspect the exception itself. There's the exception object, and really the view that I have here, it's the same view. So this is the specification of the view. Notice it's a GT view. That's a view for an inspector. But it's also an exception view, and that's a view for the debugger. Exactly the same view I'm reusing in the debugger. So when I option click on it here and see its source code, I get exactly the same method. And it's a method of the exception object itself. Why the exception? Because the exception has the context. Literally, when I mean the context, it's the execution context. So I can do stuff with that in the debugger. Time looks good. Actions are pretty much the same. No big difference here. Here, if I inspect this guy, so if I go into the debugger here, I get a retry action. If I option click on that, it's also a little bit more code, but notice it's specified as an exception action and a stack action. Stack action appears here in the regular debugger, and the exception action appears here in my moldable view. So that's why the same button appears in 2 places. So I'm reusing that as well. The code is mostly boilerplate code. So it says it's a drop down, and I got some boilerplate code to do the actual drop down. And finally, in the end here, I'm basically just redoing the action with the new count, the new number of redirects that I want to allow. So it's a little bit more complicated code, but not much more. What else did I want to show you? Yes. You can also inspect the debugging sessions. So there's something I'll show you. The debugging sessions can be configured in different ways. Notice the previous example, when I had the exception, I popped immediately into the specialized view, whereas when I opened this guy, I got into the stack view. So there's actually a configuration here. And what the debugger is going to do when it sees an object, it's going to look through a stack, or looks through the list of possible exceptions that there are, and sees if there's something, if there's a custom tool to slot in. And in this case, it does. Let me move. I know, this one is fine. So if I inspect the exception and look at the meta view, here we see the actual methods that are implementing the specialized behavior. And in particular, here's a thing called the debugger specification. So this configures how the debugger is supposed to behave. So whereas the previous example was available automatically, this one is not. So this is the only thing I have to say, don't go to the specialized view, show me the stacked view instead. And this guy is just an object which, here we go. Let's browse that guy. So this is a class for debugger exception specifications, and in the class comment, it's telling you about all the things that you can configure. Too much information, I'm sure. Just to tell you, it's not just a question of specifying views and actions, but you can also configure in a little bit finer detail how the debugger is going to behave. Right. Here's another interesting case. So here I have a snaffle, whatever a snaffle is, and it's got some data, and it has a data view. But this data might not be there. So when I define the view, I only want to show the data if it actually has data, okay? And I actually made a mistake in that code. So here we create a snaffle that doesn't have any data. And when we inspect that, I get an error. But what is this error? So let's go into the debugger. And the debugger is telling us, you made a coding mistake. And it's such a common coding mistake, we're going to tell you about it, and we're even going to make it possible for you to fix it. So the problem was, in the case where there is no data, a view is kind of a factory. So instead of saying just returning a view, what I should do is return an empty view. And there's even a fix-it that says, oh, you don't even have to type this code. Let's just generate it for you. So now if we do that and go back and execute this code, then it will behave properly. So instead of getting an error, I get an empty view. So it doesn't even appear in the list of views in this particular case. So you can actually have pretty advanced kinds of fix-its that even know about your code and repair your code for you. Oh, yes. Let me see here. Yes, in fact, I already told you this. So in this particular case, I have I'm able to only show you the code of an assert equals failure in case, so this is specified in the debugger specification, if the types are comparable, so in certain situations. So once again, the views can be conditional depending on what happens in the exception. So you don't want to throw up a view that's actually broken and useless in certain situations. So here, because I'm comparing strings, I know strings, I can really show you this nice view, so I'll do that. But if you compare different two instances of a Ludo game, it wouldn't know how to display the differences for you, so it's not going to do that. And the other one I already showed you is suppressing the automatic debugger view, so when we jump into this exception, instead of getting the list of exceptions, we go into the stack view. I already showed you that. So, summing up, the problem with generic debuggers is that they don't understand your domain. Exceptions, we can have them trigger custom debugger views. And actually, customizing a Moldable debugger can be easy. To give you some context, André Kish, who came up with the Moldable debuggers in his PhD thesis some 7 or 8 years ago, he also worked on Moldable debuggers, but there, configuring a Moldable debugger was much, much more complicated. It could do a lot more things, but it was much harder to add, to configure a debugger to do something special. And with Moldable exceptions, it can do a little bit less, but it's super, super easy to add extra behavior. The paper is available in the proceedings, of course, but everything is in gtoolkit in our open source platform. You can download it from gtoolkit.com, and you'll find in there documentation about Moldable exceptions as well. And just for fun, this page is a little slower to load. There we go. So we eat our own dog food. So this is a tree map of gtoolkit itself. All of the blue things are classes and packages where we have at least one custom view, and often many of them. We have over 3,000 views in the system. And the green things are where we also have examples. So these are tests that return objects. If I showed you a picture of how many Moldable exceptions there are, you won't see very much yet, because this is really new and we're learning how to use them ourselves. We only have about 30 examples yet in the system that we're using, but we really want to leverage this a lot more in the future. Okay, thanks very much.
We're going to do questions. Please queue up at that mic there. It's the easiest way to do it. But I have a question. Am I on here? Yes. So, conventional wisdom in development tooling work is that programmers will not do anything extra to invest in debugging tools. They were barely willing to use a debugger instead of printfs. What you're saying completely contradicts this conventional wisdom. So, how do you achieve that? How have you achieved it? Is it a cultural norm, and that people have to sort of be introduced and indoctrinated into this new norm?
Sure, so I can draw very quickly a simple parallel. It's hard to convince people to write unit tests, but if you can show them that debugging by hand, once you do that work, it's wasted and it's gone, whereas if you write a unit test, you're doing the same amount of work and then it stays part of your system and you can reuse it. That's a gain, and people do slowly get it, but you have to work at it. In the same case here, the cost of implementing a custom tool should be no more than doing it any other way. That is, it should pay off immediately. I'm writing custom tools all the time now, but it took me a long time to get it as well. But now I say, oh, I want the answer to this question. I could kind of hack up some prints or whatever, but wait a moment, I'll just define a view. It'll take me the same length of time. Once you convince people that the investment is so small, then they'll start doing it. And then they appreciate it because they see it pays off so many times, just like tests do.
Thanks very much. Well, Jonathan just asked my question, but it's okay because I've got another one.
Great.
Get the mic on, please.
Oh, it's on now. Okay, okay. Now I've forgotten what my question was. Oh, so building slightly on Jonathan's question, I feel like thank you for emphasizing that the custom tools really have to be cheap, right? That's I could tell that's super important.
It's
and
essential.
I was wondering, what are the there must be a collection of ingredients that make that possible. And one of them that I'm sensing is that you've got a shared GUI context between the debugger and the application. Are there any other things we should add to that list, that what makes it possible for these tools to be so cheap?
Yeah. So we've identified a number of patterns which are important. So in order to make this all work, you need these patterns. So one thing that's really important is the tools have to be moldable. So that's a pattern. So you have to have tools which you open up. But it's not hard. It's not rocket science. It's technically challenging, but another thing that you need is you need examples. So taking tests and have them return objects. It's pretty simple. We did it for Java like 15 years ago. We were resoundingly ignored by the community, and nobody's using it, but it's still out there and it's available. It really works. So so that's another thing. If you want to have the custom views, it should be cheap to implement them. So we have invested a lot of tooling into the graphical framework, and one thing that's unique about Block, which is the graphical framework underlying all this, is one rendering tree. So that means everything from a character to a graphic that you generate to a tool is all the same. And that's why in the slideshow, I could embed all of this stuff. You can't do that easily in other environments. And there are a few other things like that you had to invest up front, which is painful. But you know, the whole moldable development stuff, you can do it in different ways. It doesn't depend particularly on our platform. Just the idea of being able to mold these tools, you can apply it in different ways. So the work done by Philippa, for example, and colleagues in Clerk, they're applying these ideas in Clojure as well. I'm not saying they take all of the ideas, but they find the ones that are useful. And the principle of moldable development, it works.
Thanks.
Thank you for the talk. I have a question about the interference of tools and developers. So who shapes whom? Who shapes whom? So
Who shapes whom?
I'm thinking about accidental complexity and refactoring. And so the decision could be to improve your architecture to make the default tools look better, or hide complexity with new tools. And so the code base or the architecture might be unnecessarily complex. So just these two forces, like, do I write a new tool or do I invest in reshaping the architecture to make the tools I have look better, like the default stack view or whatever. So reducing indirections and so on. So what are your thoughts on this area, having these mechanisms available?
I'm going to have to interpret your question
in
in my context,
yeah.
so
Yeah.
Maybe I'm not answering the question, but one thing that's important for us is we don't believe in generic tools. I mean, some of our tools are generic, but basically if you need tools for analyzing or understanding a specific application, you'll need specific tools, because custom tools won't get you very far. So we win because we offer that opportunity. If you're going to try and apply generic tools, you'll just find they won't get you very far. So this is the only way we know that it can work.
So you have not observed any negative consequences on your underlying architecture if people start building tools instead of cleaning up code? So you can hide things, right, with nice, just thinking about hiding things with nice tools, hiding complexity and so on.
No.
You have not, that's fine.
I think we need to talk offline,
Oh,
because I think I'm probably not understanding.
That's fine, thank you. Thank you.
But I'd like to continue that. I need to understand better the issue.
Nice talk, thank you.
Thank you.
Nice talk, thank you. So how does this compare to prior existing approaches? Like, I've had to use COM, and debugging COM is impossible without Visual Studio's plugin system for their debugger. So how does this compare with that, for example, that particular example?
So I'm not, there are quite a few when we were doing the literature search for this paper, we found that there were a number of specialized debuggers for certain domains, also specialized debuggers for more domain-specific languages. There are some extensible debuggers, but all of these are pretty expensive and heavyweight to extend. And this is the only, what we found, I mean, it was kind of a revelation that it was so simple, that this approach really gets you very far with minimum effort. Just the cost of extending a debugger in this way is so simple compared to the alternatives.
So do you
I haven't seen anything like that.
Do you find the notion possible that you could take this and map it onto the Visual Studio extension system, something like that?
There's no rocket science here. It should be super easy. You should be able to open up any debugger and apply the same approach. It's just a few hooks. Yeah. I think anybody who's developing tools like this should be able to take this idea and run with it. It's probably a shorter, I can't imagine it would even take a week of development effort.
Wow. Okay, thank you.
I'm guessing.
Okay, thank you.
Yes.
Okay, so thank you, Oscar. The next paper is Michael Homer, Reclaiming the Unexplored in Hybrid Visual Programming. And I can already see that my question is going to be, how do you reclaim the unexplored? Does that mean we already claimed the unexplored?
I would say the title isn't exactly what I want it to be.
Sorry, go ahead.
All right, so this is Reclaiming the Unexplored in Hybrid Visual Programming. I am Michael Homer. Should do that. We'll see how the title bears out as we go. So I have basically two arguments that I want to make here. One of them is that visual programming environments as they currently exist are too similar, are too samey, are too wedded to recreating the same models of programs, the same models of programming over and over in slightly different variations, but otherwise all pretty similar to one another. The other argument I want to make is that it should be possible to look at the same piece of code in different ways using different representations and to edit, manipulate, run, simulate that code in any of those, all within the same system. So it should be possible within one single system to look at the same piece of code in various different ways at different times. I'm going to flesh out those arguments a little bit, and then I'll show some pieces of a prototype I made that explores some of those areas, and maybe make the argument that this is actually relatively easy to do. First up, let's have a look at visual systems and what I mean by sameness. So there are a few common patterns that come up again and again in existing visual systems. One of them is the node and wire environments, so boxes with lines between them. Those lines are edges or vertices or wires or whatever, and that's a graph. It represents the control flow or data flow, or sometimes both, of the program. You edit the program by actually editing the graph. The changes that you make to the connections are changes to the control or data flow when you run the program. There are a lot of these systems. People keep making more and more of them. A few of them have taken off and had some relatively significant success. A big example would be Unreal Blueprints, but there are also some other more specialized things. You've seen things in LabVIEW, you've seen things in other cases as well, particularly sort of music, arty things sometimes. But by and large, those are tending to be too clumsy, too awkward, too large to really be practical. People keep trying them. This time will be different, and it's not different. Another common pattern is the sort of textual analogs. So I'd say block-based programs are a very obvious example of that, where what you're really doing is editing an abstract syntax tree of a textual language. And whether or not there is any actual textual language that you ever serialize that out to, you're going to eventually have something that is essentially a syntax tree. You're going to be editing something that is describing the program in the way that a conventional textual language can do. There are some other approaches that also do more or less the same thing. They don't present it in quite the same way, but where ultimately what you end up doing is changing the syntax tree of something that is a more or less typical backend bit of code there. Most of the time, What these do is they replicate the behavior, the model of the common, successful, popular, mainstream programming languages that you see people using in the textual world all the time. That means they're taking with them the general structure, the general semantics of those languages, and they're adding these visual things on top of it, which have their own costs, their own benefits, and so there are trade-offs being made there as well. Both of these common models are useful sometimes. Both of them do have value. What I'm going to argue for, though, is that we should have more and different things going on as well. We should have more varied presentations. We should have different views that are more dramatically different. We should have approaches to it that make more use of the full range of things that a visual system can provide that a textual system can't. So rather than just editing things by dragging shapes around, which is basically what you do for both a block-based system and a node and wire system, we should be using all of the available dimensions. So spatial layout can be semantically meaningful. We can use color and we can use movement. We can use change over time in ways that a textual system just can't. We should be making systems that make more use of those things. And there are some of those that are around already. We should have more of them and we should be using them all the time. We should have more varied semantics. We should be looking at different approaches to programming that a visual system can help out. So there are a lot of approaches to programming that have been tried in the textual world that have not been as successful as your Javas, your Pythons, even your sort of typical functional programming languages have more success than a lot of models. And it's interesting to think about why that might be and whether a visual system is able to compensate for some of the drawbacks that might have led to some of those systems not taking off to the extent that they might have liked. It may be possible to, in a visual system, cut off the limitations while still exposing the strengths, still exposing the reasons that people wanted to create and use those systems in the first place, so we can make use of those benefits without having to pay all of the costs. So for example, fourth is a language from the concatenative paradigm, called because you concatenate things together and you get a composed program. And those languages are sometimes known as write-only languages because while it's quite straightforward sometimes to write new code in it, looking at existing code can be completely incomprehensible because you have to mentally simulate the way the language works. Think about what are all these functions doing, how many arguments do they have, and if you get it wrong, then your entire understanding falls over. A visual system could present that in a more straightforward way, could expose information to the user that would make that more comprehensible. We can cut off some of those costs while retaining, hopefully, some of the benefits of it. We should explore that for all these different models and other models as well. There are lots of paradigms that have had no exploration at all. I think these ones up here, there have been some visual systems that have worked with them. There are other models that have had none at all, and we should be trying to explore all of those and seeing whether or not they're useful. At the moment, we just don't know because no one really tries it. That's my first argument. My second argument is that we should have multiple representations in the same system. So there are a number of block-based systems in particular that have a sort of parallel textual and block-based view that you can either switch between, like in Tile, Grace, and Droplet, or that you can see at the same time, like Polyglot. And there is some good reason and some research to show that just the mere fact of having two representations here is beneficial in some ways to the users. There are also other alternative approaches that don't look as much like code on each side, like the sketch and sketch on the bottom, that you can edit on both sides and again edit the code. These multi-representation systems allow us to have different interactions and different affordances provided to the programmer when working with the same code. You can take that tile grayscale at the top, you can edit it as blocks, you can edit it as text, you can go back and forth, and you can do different tasks in a different view if you want to. But when I'm talking about multiple representations, I'm not just meaning let's have 2. I'm thinking let's have 10 or 20 or more all in the same system, which will allow us to specialize, will allow us to have a much greater variety of different approaches explored for the same code that can be suitable at the right time. So why would we want that? Well, each one of those views can make its own different trade-offs. It can decide to foreground different aspects of the code itself, of the data the code's working on. It can choose to make different interactions available. It can give us the ability to make different changes, to inspect things in different ways, without having to commit to that, using that for the entire system or for all time. It means that the user can choose the right view for the task that they are trying to work with. They can pick out the particular view that helps for the particular thing they're trying to do, They can do the thing, and they can move on and then not use it again. That means we can get a much wider variety of presentations all available without any of them needing to be quite so load-bearing. It'll be possible for us to try out some very special purpose views that have very specific reasons to use them and incorporate them alongside the other more generally applicable approaches as well. It's possible there'll be different audiences that our different views can work with that can also help us to make better use of our code and of our coding time if we have other people elsewhere in the organization writing code that are not programmers, but they need to understand what the program does. We can have a system that can present that in a more accessible way for them, maybe even a more editable way for them, potentially, that is still fully integrated with the system that the programmers themselves are primarily using. The other point, though, is I talked a lot just before about how we should have more varied representations. One thing that comes with having a multiple representation system is experimentation becomes cheap. Having new representations has much lower risk and is a much lower stakes proposition. That representation that I make doesn't have to be load-bearing, doesn't have to carry the weight of the entire system. It can just be something that we try out speculatively. We can put it in there, it can be used for what it's good for, we can try to find out what it's good for, and we can just ignore it for the times when it's not so good. So we can explore a much wider range of things at a much lower cost and with less work, less risk. Any multiple representation system is at least as good as the best representation on its own, because if nothing else, we can just use that one all the time. But we can also have other views that can compensate for any drawbacks that best view has as part of it. That means we can uncover some hidden gems, we can include some limited purpose views that have very specific use cases, and that comes as part of the system essentially for free. It's relatively cheap and relatively easy. I think that is a valuable thing that we should be encouraging and we should be exploring more of to allow us to explore more of the space in general. So that's essentially my argument here. What I'm going to show is a bit of a prototype that I made and some extracts from that prototype that are going to illustrate some of those arguments, some of those points that I've made here. This system has several representations in it. Maybe not all of them are good. In fact, almost certainly at least one of them is not good. But they're all there, and we can try them out, we can explore them, and we can find out whether they are actually valuable or not. It's a switchable system, so you have a program on screen, you click a button, and you have the program in a different view afterwards. It works by animating those into place, so whatever is in both views will smoothly move between, so you know that this is the same element in both places. It has some quite contrasting paradigms, some varied purposes, some varied interactions that it supports. It's possible that there is a greater range of things that it can do there, but I'm going to show off a few instances that are going to cover a range of things that support the things I've been arguing so far. So here we have what is essentially a very boring concatenative language, a fourth-like language here, that is highlighting already some of the potential difficulty of understanding what's going on here. One of the difficulties is that you have to know what the arithmetical of the functions are, what the outputs are, what order they come in, all those things there. And in a textual system, it's just difficult to do that. But what we can have in a visual system is we can make this interactive. We can allow it to highlight that information to us, to show us where these arguments come from, where the outputs are going, and to offer affordances for inspecting the functions themselves, for inspecting what they do, for inspecting where they come from. We have that ability that we don't get in a plain text system. We could layer this on top of a plain text editor, and it would be fairly similar. We can also have a much more contrasting approach. So here we have a two-dimensional grid layout here, where the spatial layout is actually semantically meaningful. This is the same program as before. It's a little toy program, basically not a very good one, just so we can use some of these features here. And it's going to show us that in the middle here, add is taking in 5 and 4 from above it, and it's producing 9 below it. So the spatial layout is actually showing the structure of the program and showing which values, which arguments are being consumed by what, which values are being produced, and it's showing the actual values themselves. We could also have different data coming in, we could scrub through that and look at different approaches, different results that came out from different input data as we went through it. We can also go a little bit further from this. We can switch away from this view entirely. This one is good for some things, it takes a lot of space. We could switch to a different view, maybe a view from an even less common concatenative paradigm that virtually no one has explored before or back into our normal one again. We can also switch this out again into a sort of essentially a node and wire system. So we can pop over here and we can look at this as a node and wire system. Those do have value. They show things that other views maybe don't highlight as much. So they're not inherently bad, they're just often not great as the only way of doing it. We can see here some of these semantic trade-offs that I've made in letting those representations coexist. So in particular, we can see that all of those function nodes there, essentially they're in columns going across the page there. Those columns are the same columns as the rows of the previous grid view that we had before. And so the structure of this node and wire system enforces that we have our edges always going from left to right. It inherently layers these things so that we have the ability to have this wider range of views of the same code here. That's a trade-off. That's a cost that has been incurred to allow us to have all these representations together, but there's no actual semantic cost of that. It doesn't change what you can express. It's just a structural change in the way that we present it and the way that we store it. The different functions in the system can settle into different views. I could have one that was looking at things in this way, one that was working in the concatenative way, one in the grid way, one in any of the other views that are available here, and they could all interact as equals. They all interact under the same shared semantic model here. That means that we have the ability to settle different parts of the system with different users in different views, or different parts of the system that have different things that we need to do with them into different views, as well as switching between them at runtime for the same code. The semantic model here has a number of oddities as part of it because of the domain I'm working with for the broader project here. And one thing in particular is that it's possible for a function to have alternative results produced. So it can produce more than one result that then gets projected through the rest of the program, and we evaluate the whole program with each one of those alternative results. The idea being that we have potentially one column of data that has many things inside it. We're going to splay it out. We're going to see some examples of what we can do with that as well. But the semantic model as a whole is a compromise between a lot of different things. So there's a trade-off that's being made no matter what we do here, but we can make things that are able to cover a very, very wide range of different things. Maybe sometimes that range can be a little bit too wide. So we can also have this view here, which is one that people suggest when you describe the way that the graph layering and so on works. They describe it in advance. I made it. I've tried a few different versions of this. I'm not sure that any of them are good. It has the unusual combination of benefits of being both very large and conveying very little information. So this one quite possibly just is a dead end. But we can make these kinds of speculative explorations. It doesn't have to have the entire system rest on this one view being able to carry the weight of the entire programming system here. I can add this in here, and if it is useful for some audience or for some purpose, then it's available, it can be used. If it isn't, then it will probably wither away, maybe eventually it'll be taken out. But the ability to make these kinds of speculative explorations is, I think, a valuable one, and one that we should aim to create for ourselves, even if sometimes the things we make are more cautionary examples than actually valuable ones for ourselves. I'm not sure it's good, it might be. I think it's new. I think there might be a reason no one's done it before, but it's there, we know about it, we can see it, we can see and we can find out what's going on with that. One more special purpose view here. This one here is aiming for a certain kind of debugging that someone might do. I mentioned that we have potentially multiple results here. Now this here is, I would say, not a good design for a square root function, but for the sake of a tiny example, our square root function returns both square roots. And we can see that we have the program sort of forking. Each of these horizontal splits is forking into a different line that evaluates the rest of the program using each one of those return values here. If you're familiar with JQ, the JSON query language, that also works essentially this way. It's list monad, it's a bunch of things here that you can look at in this kind of a style. This here is a view that is available as an ordinary view as part of the regular system. It's just an ordinary view of the code, just like all the other ones, but it's there for a particular special purpose. It's here to allow us to do some debugging tasks. And we can inspect it, we can interact with it, we can offer additional affordances as part of that, but it's fundamentally just a part of the program itself. It's not a different view layered on, it's not something we can explore separately, it's just one view of the same code we're working with the entire time that offers some additional features for certain tasks that we might be trying to do at any given point. There are also some other views here and some other alternatives here, but I'm not going to dive into too much detail now. I'll finish though with a bit of a call to action, which first part is we should explore more. We should explore more even if things we're exploring are potentially bad. Maybe even especially if they're potentially bad. And I think in particular, we should build multi-representation environments, not just because they're good on their own, but because they make that exploration easier and cheaper and safer for us to do. It gives us the opportunity to make more explorations without having to invest in the entire system for just that one model. Finally, just give it a go, make things, and then tell us what you found. Even if what you found is this radio view is bad, make it and then tell us about it so that we all know the radio view is bad. Because there are a lot of explorations out there that could be done, that one of us might try to do, and then we'll discover, well, once we've made it, it wasn't as useful as we thought it might be, or it didn't turn out to be useful even when we thought it wasn't going to be. But try it, make some more things, explore a lot more of the space that these visual systems can give to us, and actually create them, talk about them, tell us, communicate with the world, and let us know what's available and what is and isn't a good idea in this world that hasn't been explored so far. With that, I'm going to thank you for your attention and invite any questions anyone has.
Trying to figure out how to turn, oh, it's on, okay. So having seen visual programming environments in my past lives with Smalltalk that have failed. And then when I was at Tech Labs, or Tektronix, trying to do visual programming languages, there's some things that they don't do well, and I just wonder if you've had some thoughts about visual ways of programming. One thing is scale. So I can see a tiny example, and I can comprehend that, and I can, you know, from a student point of view, but I've actually seen really badly done visual programming environments where once you get like 400 lines between things, it's incomprehensible. So that's one issue. How do I deal with scaling and scoping? Because I think programming or modeling is how, you know, an environment that supports visually doing that would be kind of nice, but at some point you're just, it's not just that you need to go in certain views, but it's the whole idea of programming that way becomes incomprehensible. So that's one problem about how do I navigate a larger program this way. Second thing is dealing with recursion and timing and loops that go back. And visualizing those things, particularly let's say if you're doing graphics animation or things like that, it's really hard to kind of visualize those. So I just wonder if you had any thoughts about those two kind of problems.
Yes, I think one thing that we can do for scaling is when we have multiple representations, it's possible that some of them can allow us to ignore parts of the program, can allow us to see some of those things at a larger scale without having to have the entire thing presented. Like one of the node and wire issues is you have 400 lines, it becomes impossible. So that is a trade-off we can make between different views, but I think the bigger picture of it is I don't know that anyone has created the views that are good for that yet. What I'd like people to do is create them and tell me about them. So I don't know that part yet.
Fair enough. One thing that drives me nuts is like people who think are in love with Prezi and they go zoom around. I get vertigo looking at that. So anyway, just don't do that.
That's good advice too. Yeah. Yeah, I think that the ability to have different views is probably helpful for these things, but I don't have all the answers to that yet. What I'd like us to do is explore more, and I think that we've run into that problem and then decided not to carry on too much. And I hope there are better solutions to some of these things. One thing we can have is we can have text representations as part of this that can cover some of those things in a broader way if we want to.
Okay. I'm sure this doesn't surprise you, but the idea of having lots of different kinds of views resonated with me. My question is, how hard was it to implement those views? And the subtext is, can you imagine a platform or an infrastructure that would make it easy or cheap to come up with lots more views of the kinds that you were thinking of?
I think I might have seen one just before. I think that the cost of making an individual view here is not that high. I rebuilt the system and pretty much entirely since writing the paper. And I'd say making an additional view is something that I can do in a day or so, including all the animations and so on, just happens. Building out the infrastructure to make that doable is more complex. but it's relatively easy to add new things into this if you want to. I don't think it's a high cost thing here, but it is work, and it is a lot of fiddly detail doing layout and stuff. So it's still doing sort of graphics work somehow.
I was just curious because the example that you gave was like a numbers, obviously very pure functional stuff, and I was curious about if you've considered different visualizations for imperative side effect type stuff, like you have in the examples you were contrasting against the beginning, you had like control flow, and then there's like alternative visualizations, like if you know state charts, they're like based on finite state machines.
Yes, yeah, so the overall bigger project here is essentially a data pipeline system. So it does have a forwards flow essentially all the time. So not in this model, no. More generally, again, what I want is for people to explore those things, because I think that in particular control flow is just not something that these systems have dealt with particularly well, other than by falling back on basically what is text and what is a control flow graph directly. So no, I guess.
Hey, great talk. Do you see a use of views that you can't program everything in, but you could program certain things really well? Like a restricted scope so you can use better abstractions and things like that?
Yes, 100%. I would like that. I think it is basically a good advantage of a multi-representation system is you can have views that really are good for exactly one thing, and that's it. And you don't have to have the whole system built that way. And what I'm, I guess, arguing for is the ability to make those is actually valuable. That what we need to do at the moment is we make things that are good enough for everything, but not actually good at anything. And we can specialize more, and that gives us more opportunities there.
Yeah, okay, great, thank you.
Well, I have a question. Marcel, do you want to come and set up? Well, so I love what you're doing here. It's really nice, and I love your call for 1,000 flowers to bloom. And I'm certainly guilty of having done these sorts of experiments myself. Maybe can I make just a suggestion, which is that the next step, it's great to call for more people to do it, but we have to have some sort of a context in which that happens. What's the next step after you have this? And maybe it's, look at the artistic world where people come together and do showings and then design crits for each other and things like that.
I would love that, but.
So, okay, well there you go. That's your next step, right?
I'm not good at organizing things. Yeah, I think that'd be great. I think it would be good to have, to look at these things as more than just, can it do something specific, but can we think about the other benefits that come with it as well.
A place where we can look forward to coming and show these things to each other and give each other feedback, because, the serious professional programmer world is, until you're at scale, they have no interest, right?
Pretty much. I think that
So
things like Live and Paint kind of try to do that kind of stuff. Live actually does do that kind of stuff, I guess, and Paint always has the design critique stuff in there, but I think that it's hard to squeeze those things into both industry and academia. So something a little bit hybrid is probably required there.
Thanks. Right, our next speaker is Marcel Viher. Is that right?
Yeah.
Viher.
Just like the wire.
The wire.
Yeah.
Who is? Oh, okay. Oh, yeah. He's going to take us beyond procedure calls, and since we all know that procedure calls are a requirement of all programming languages and are necessary and sufficient, he's going to explain to us why that's not true. I think, right?
Well, we'll see. The title of the talk is, and the paper is actually a riff on Mary Shaw's seminal paper, Procedure calls are the assembly language of module interconnect. Connectors deserve first-class status, and I see Mary Shaw is in the room with us, so no pressure. We'll see how much I've hashed things up. And my name is Mark. Yeah, okay. And I'm a post-career PhD student at HPI in Potsdam, working with Robert Hirschfeld and Marcel Träumer. And well, we'll see. What I'm talking about is a programming language, an architecture-oriented programming language called Objective-S. It used to be called Objective Smalltalk, but that was too long, and it's still too long, and it's a bit of a joke, but anyway. Obviously it's a development that's based on Smalltalk, but it needs a little bit more because, I mean, in my career I've noticed that programming is just too low level, and it's too much work, and I think that software architecture is sort of one of the things that's missing, and one of the things that's missing is being able to actually express the architectures of our systems in the code. Instead, we have to write procedures that implement that architecture. And I think this has been, you know, I'm not the first person saying this. This has been said for a long time, and I think I might have had a crack at solving this. And the key is actually combining software architecture and metaprogramming, particularly of the style of metaprogramming that's in the art of meta-object protocol discussed there, where we take the object-oriented principles and apply those to the metaprogramming problem. So our metaprograms are also object-oriented frameworks, and the programming language comes out as the induced domain-specific language that is induced by the framework. And there's a little bit of an addition. The thing is implemented in Objective-C mostly, which, you know, doesn't make it that different because Objective-C is just C and Smalltalk smashed together. But the key is I don't add these things to Smalltalk. I generalize from Smalltalk, right? So because when we have components and connectors, the other things that we tend to have in programming, for example, object and messages, well, that's a component and connector. Same with, you know, algorithms and data structures, pipes and filters, files and paths, resources and URLs. So basically, Objective-S takes the two components we saw before, the software architecture component, which is the conceptual framework, and then the meta-object programming system, that's the implementation framework, and then builds everything else on top of that as specializations. And of course, one thing we learned from Smalltalk is that the implementation hierarchy does not have to be the same thing as the conceptual hierarchy. So in terms of implementation, we have the procedures. We're good. It's all built from procedures. And the way to get there is basically when we saw, you know, when software architecture research was done, there was a lot of field work actually in terms of what, you know, how are we actually building these systems? What are the connectors in the wild? And one of the papers that I used is towards the taxonomy of software connectors, and there is quite a bit there, right? And because it's a taxonomy, it's actually structured, so that's really useful. And what we see is in the top left corner, we see sort of some of the columns. There's a type, and when we see the types, and there's values, right? So we have very few types, and then we have lots of values for those types. And that's really actually essential, right? Because there's lots of complexity over on the right, and there's actually only a few things on the left. And we can then just ignore the entire rest and actually scrunch it down a little bit and then just plot those in 2 dimensions. So we have a subset of the types running vertically, and then on the right-hand side we have variants of those particular types. And that's a really interesting table, I find, because there is a lot of complexity in software and how we build software, and it just reduces away. And if we look at this table right, we can see that the problem of adding software architectural description may actually be simpler than we thought, because we don't really have to add anything. It's already there. We just have to look at it differently, because the variants that we have on the right are actually things that are usually in our programming languages, just not in every one of them. We have particular examples that are in particular programming languages. For example, some programming languages have procedure calls. Other programming languages have synchronous message sends. Other programming languages have asynchronous message sends, and so on and so forth. And so the problem with software architecture becomes actually expressing software architecture in code becomes the problem of variation of programming languages. And that's what we have meta-object programming for. And so we don't really have to add anything new. We have to just take languages that we already have and make those polymorphic in a better way than we do before. And in the other direction, we never really had a good model, I think, for how do we do metaprogramming. We have all sorts of models, but syntactic macros, or the meta-object protocol of clause was pretty close, but then that was fairly tightly defined. And so we can make variations of object-oriented languages, but nothing really that spans. And I think so, in my opinion, these two areas actually need each other. So we get better metaprogramming through software architecture, and we get better software architecture through metaprogramming. And so that's the approach, basically. That's the core idea. And then we just start doing things. Like, we add a meta-object protocol, right? And it's in each case, it's in Smalltalk syntax, and it's not the complete meta-object protocol, but it's a sort of an extract. So for the procedure call, we have the send. We send a message, and we can have different types of meta-object protocols messages there. Send would be a synchronous message, and we can have an asynchronous message, and so on and so forth. For data access, it's basically the set the value, get the value. For data flow is just here's some value, some object, write it to somewhere, and that's really it. And once you have that, we can actually then support that at the language level. And so and have syntax for easily accessing anything that conforms to the particular meta-object protocol. So anything that somehow can be sent a message, we can use message sending syntax. Anything that can has data that we can access and we can either get or put, well, we have syntax for that. Anything that we can just shove data at, well, we have syntax for that. And there's sort of a hopefully a pull effect that once you have these two things defined, it becomes very beneficial to actually conform to that particular meta-object protocol if you have something that's sort of in that shape, because then you get language access. And that makes things very simple for users to use your stuff. And of course, since it's no longer 1980, we can use left arrows instead of weird combinations. And yeah, and so the next step is, since all these we've made all these different kinds of things conform to the same protocol, it now becomes not necessarily super easy, but certainly straightforward to connect them together, because they all have the same shape. And once things have the same shape, we can just keep plugging them together. And also, we don't really have to introduce much special syntax to do that, because there's just one action. Please plug these two things together. So we can just take the right arrow, which works for most of these, except for the procedure calls or the message sends, because we kind of already have that. It's not really clear what we can add to that, although there may be some things we can add to that. So, and once we have all that, the purpose, of course, is can we actually make, or the question is, can we make different architectural styles as convenient as currently we have, procedure calls, message sending, because that's kind of where we want to be, because right now, the only architectural style that has good support in convenient support is procedure calls, message sends. And so you can have any color as long as it's black. Well, and that's and you have a choice. You can either make your system conform to that, or you can make a good architecture, and then you have all sorts of indirection in your system that you cannot get rid of. And so the first one, well, that's the procedure call, so we don't need to do that much. Of course, except that, of course, we have the special case that the procedure call architectural style is also what we use to implement. But we do a little bit. We have higher order messaging. That's a paper from DLS, I think, in 2002 or something. And basically, it's a message that takes a message as an argument. And the prefix message controls how your messaging works, how the messages are routed. And some examples of that are, we have a standard hello world, standard out print line hello world, and then we can control how the message gets routed. For example, here we have the message gets sent with multiple arguments. That's the first one. So we have number of messages sent can be changed. We can have this number also in the receiver or in arguments. It doesn't really matter. We can also control time or synchrony. Normal message sending is synchronous. We say, well, maybe we want it asynchronous, or then we just have a prefix message that says, well, please send this asynchronously. Or we say we want to send it after a second. That's actually used in the, what was it called? I forget. Kannst du mir kurz helfen? It's the system that Andreas was working on. Okay. Yeah. And we can also encode some more complex patterns, right? For example, if response just says, well, if the receiver understands this message, then send it, otherwise don't. Nee, nicht tweak, dieses Multi-Agentensystem, distributed. Croquet system, yeah, sorry, brain fart. And actually, there's some further architectural patterns that you can encode, but slides. So we got that. Data access is actually one of the more interesting ones I found, and it's also the one where a lot of this was started. Back in 2003 ish time frame, I was working for the BBC, and we had a website system, and I decided I wanted to see if we could, in the rewrite of that system, just mirror the external structure internally in the system. And that turned out really well, and then I wrote it up as in-process REST. And of course, REST is a architectural style that, whether you like it or not, it certainly seems to have worked somehow. We have a fairly large distributed system that's built on it. And we're using it more and more to also structure systems. I mean, for example, microservices are a way of structuring systems using REST architectural style, except all of them then have this packaging mismatch of you must actually distribute the system. Now, wouldn't it be nice if we didn't have to distribute the system in order to do that? And the components to accomplish this are polymorphic identifiers. Basically, you can use URIs as the identifiers in your code. Storage combinators that resolve this and are also very pluggable, very composable, because the REST interface is just a couple of verbs. and that makes things composable. And then you get first-class references out of that, which I'm actually not going to go into. So polymorphic identifiers, the idea here is we have a lot, when we access data, unless it's the built-in language kind of access, we can, if it's that, we can just use the name, yoo-hoo. But if it's anything else, we have to wrap it in a procedure. And so we get this great variety of procedures that all do exactly the same thing, just for a different type of access. And well, you don't really have to do that. If you have URIs in your system, they can all look the same, except for the one part that says, well, please look here. And I think you can see that in the two right, the rightmost columns. And of course, it's important that this doesn't just work for built-in domains. You can always you can define your own, and actually that's where I have found this to be most useful. So basically, for your own domain, you say, I want a certain kind of way to access this. I make a store that can handle that access, and I define a URI pattern that accesses that, and I plug that into my name. And of course, once again, these are composable. So for example, in Wunderlist, where I used this, this was the store hierarchy, right? And so all the ones that have arrows leading out are storage combinators. That means they're stores that take another store or several stores and combine them somehow. And what's wonderful is you can just plug things into that hierarchy and take them out. And for example, there's a keychain access right there, right? So there's a switcher that says, well, if this is sensitive data, put it in the keychain. And the rest of the system is none the wiser. It doesn't really have to know about this. And Hello World on the web, of course, obviously since it's in-process REST, web programming is kind of very natural. And so the first line is just, we have a dictionary that says, has the world value for the hello key, and then we just hook that up to a web server, and that will serve this onto the web. And so if you type the URL, if you give it a URL with wherever you post it, wherever you put the server, and hello, it'll return world. And the second one is more flexible. You give it the URL greet / and then your name, and it'll return hello and the name that you gave it as a parameter. And that's these are jet lag is really getting to me. Property paths, that's what I called them. So basically, you can, a lot of programming languages these days have properties, and basically what these just do is extend them so you can have full paths that you can specify. And one of the really nice things, as I said, is you can just switch things around. And for example, the previous example that we had of the fairly complex store hierarchy for Wunderlist, for testing purposes, we don't want that, right? We don't want the unit tests polluting our keychain, and we don't really necessarily want to go access disk. So replace it by that, right? And again, the rest of the system is none the wiser, because we just have its stuff in memory. And of course, when I showed you these more complex Wunderlist store, that was actually a lie. It actually looks like that. And again, during the development process, we could just plug things in, and it would just work, and it's all in process. I asked one of my colleagues for the storage combinators papers, what he estimated what the benefit was in terms of development time, and he told me it's about 2x. So I put that in the paper, and it's like, okay, good. I met him a little later, and he said, oh, you know, when I told you 2x, that was a lie. I said, oh shit, what did I do? It was more like 10x. I just didn't think that number was believable. So that was data access, data flow. That's just very simple. Again, that's the super simple one, Unix pipes and filters. We all know and love, except that, of course, there's some issues when you actually want to reuse Unix pipes and filters from other systems, because you know you have to start processes, you have to serialize, deserialize the data, you have concurrency issues. But you get very concise programs. There is the famous Bentley's challenge, where you know what was that? John Bentley from the Programming Pearls. He challenged Don Knuth and Doug McElroy to do some word counting, I think, task. And Don Knuth had this wonderful 12-page, you know, literate program, and it was just a beauty, right? And Doug McElroy had a 6-line shell script. And it was only 6 lines because he put each command on a separate line. Right? So you can get, you know, it makes a difference. And the other example was Nile Jazeera from the STEPS project, right, where they did, I think, a rendering system, computer graphics rendering system in 400 lines of data flow, which is really impressive. But again, you also have these problems that very often you have this packaging mismatch. So my answer to that was polymorphic white streams, which I wrote up. There's a paper on that. And basically, it's object-based, so you know, a bit like PowerShell. It's completely, its default mechanism is completely passive. So you know, you can add activity, you can add multiprocessing if you want to, but you don't need to. What makes it a little bit more magical is the double dispatch. So, and that's what the polymorphic white streams paper actually talks about most of the time, that it can decompose and recompose object graphs on the fly and combine that with stream processing. And one of the really cool things about data flow in terms of usefulness in larger systems is that because it's based on the data flow, not on the control flow, it's concurrency agnostic. So even though the basic system happens to be synchronous, adding asynchronous elements is easy, and it doesn't change the semantics of the composition much at all. It just changes exactly, you know, what happens when. And again, some examples. The first defines a filter. It's the greeter filter, and the little pipe symbol says that please make this a stream message. And yeah, it writes the hello with whatever you passed it in as an argument to the next filter. And the idea was, again, it's a convenience thing, and convenience is really important, as I think, you know, some of the previous presenters also rightfully noted. And therefore, defining a filter should not be much more strenuous and much more arduous than defining a method usually is. Because very often people want to use these alternative architecture styles because they should be better, but they're too complicated to express in current systems, right? And then if you want to fill that right, I stole that actually from C++, so yay C++. But since I already had all the arrows used up for other stuff that I thought were more important. Because, for example, right next there is the right arrow for just, you know, we combine standard in, hook that up to the greeter, and then hook that up to standard out. And I think, you know, that's an architecture, and I think it's pretty obvious what it does, and it's pretty concisely expressed. And again, the data flow architectural style seems to be extremely composable. What I found is that it just really works extremely well as glue in all different parts of the system. Not so much by itself, but just hooking things up together. For example, the next one is just, you know, have a text field instead of standard in as the source, and you hook it up just the same. It doesn't really make a difference. And we have interop. Obviously, we have the interop with objects. We have interop with Unix pipes, and there's interop for the Al Jazeera system. I actually wanted to see if my idea of having these passive filters works in other contexts just as well, and it turns out, yes, it does. I replaced one of the filters in one of the Nile demos with one of my own, and it works quite nicely, and it should play, yes. So, yeah. And oh, this was one of my stretch goals, was being able to implement data flow constraints basically within the system. Oh, I need to finish? Okay. 3 minutes. Okay. Well, data flow constraints also work. Yeah. And one of the interesting things that came out of this work was that usually data flow and events are apparently considered very different architectural styles in terms of syntactic and language support. I found I could handle them using the same mechanisms. So internally, we have notification protocols that basically connect an event system to messages of classes. So you can just say, I have a class that implements a specific protocol, a specific interface, and then I can message that interface, that protocol, and it'll just message all the classes that implement that. And event buses work as you would expect, basically just like a filter. And those were the styles I was going to have a look at. And then just a quick note on how the connect works. I have polymorphic connection. So the first image is sort of the, so the arrow is not actually the connector. That's kind of weird. In the theory that I looked at, the way it works is the full model is you have a component, the component has a port, you connect the port to one of the roles of connector, and then you connect another role of that connector to the port of a component. Writing that out every time would be extremely arduous, and it turns out that most of the time you don't have to. And in fact, most of what I've, in practice, when I use this, I find that the form at the bottom is the one I use the most. Because if I say these two components, I want them to be connected, the ports are obvious and the connector is also obvious. If they're not, you can go back and disambiguate, but usually you don't have to, and that makes a huge difference in terms of convenience. So we got that, and basically we're back to the overall picture. There's a bit of outlook. There's lots of things that could be done. There's debugging that I think can work much, much better when you have a higher level model of your system, rather than having to recover what the system is doing in terms of your intention from the procedures you wrote to implement that system. Multi-program systems are very close, and I think will be really, really, really interesting. And of course, you want to do more connectors, more variants of the connectors. Okay, maybe we can do something about structure, definitions. Yep. And yep. That's it.
So I have one question. It seems to me, I was thinking about the command query response architecture style, communication style. One thing that's kind of common that you might want to do is create projections for different contracts between things. And have you thought about ways of taking stuff and making projections as part of? So in essence, it's not like I have the API with this type, but I want to be able to have support for generating projections as a programmer. Do you know what a data projection? Yeah.
Yeah, I mean, I think that it's a slightly different area, right? But I mean, I would like, I mean, if there's some prediction from that's going on, I would like to probably express it as a maybe a different connector.
Yes, and that would be nice to be able to have some support for understanding the projections I need to do. That's what I'm saying at that level that you're talking about. And then another thought was, what about data mesh architectures these days, which are, you know, it's not simple connectors. It's, anyway.
Yeah, I mean, so far, this was getting the simple stuff done, and now, you know, here, that type, there's lots going on, and I think maybe when we have a start, you know, we can start adding stuff and do the really also just larger aggregations. I haven't really done,
Okay.
right? But I think this might be the starting point for actually doing that.
Yeah, I think it's really cool, but I'm just asking for more, so I'm sorry.
Thank you. You know, please do stuff.
Hi. I was just wondering, are you at all familiar with sort of the modern JavaScript meta-object protocol since 2015?
Very little. I do know that I think sort of in the some of this, I think the higher order messaging stuff got in there in a slightly different version.
Yeah, I mean, the basic idea behind it was in designing the language at that level. There was lots of weird things implementers were doing with special types of objects and had special semantics on field access or method invocation for special cases, particularly in like the DOM and such.
Yeah.
And these were things that couldn't be reproduced in JavaScript code. And so one of the design goals was to be able to self-host any of that sort of stuff. But it just occurs to me, I mean, it's another example now of a language with a fairly complete meta-object model, and it might have some utility in what you're looking at here as another thing to contrast it with.
What I've noticed is that, I mean, also Faro has some specifics. Is they tend to, when they do data access meta-object protocols, they tend to be extremely field-specific, and that tends to be limiting, I think. Now, I think you can take this and plonk it on top of that. I'm not sure the other way works around as well.
Yeah.
Okay, thank you.
Okay.
Yeah.
So, thank you for taking this on. I'm really happy to see how far you have pushed it. I have a small question and a large question. The small question is an example. In their paper on the specification of the A7, Parnas, Clements, and Weiss, focusing on separation of concerns, created an example of what they called a data banker model in which you could do a single kind of data access, and the information hiding mechanism would disguise whether that was a direct access from memory, a query from a sensor, a bunch of other things. I just wondered whether you're familiar with that example, and I'd be really interested to see how that example works out in your system, because they came at it from a very different standpoint, but it has a lot of the characteristics that you're after, although I think they may be moving them to a different level of abstraction. So it's hiding the underlying mechanism by which a piece of data is estimated or retrieved or fetched. So I'll just... I don't want to dwell on that if you haven't already thought about the example, but I'd commend it to your attention. The larger question is about the other assumptions that come along with a connector. So for example, in pipes and filters, one of the things that I always found perplexing about Unix was that there's no type checking on the streams. The filters do not come with a specification that says arbitrary text stream. I'm expecting a line break every 5,000 characters or less. This is really something else. And that for me is a piece that's missing from pipes and filters, which is a further restriction on the combinations that are legal. Another example of a further restriction in pipes and filters is that if you want to do composition of function, that is, this filter computes F and that filter computes G, and you want to compute F of G, you can compose them, but you only get that assurance if there's no out-of-band communication between the filters. Have you thought about ways to incorporate this kind of additional constraint on the use of the connectors as part of the validation of the system as a whole?
Not much. Certainly type checking connections is very interesting. I know very little about type checking, and this was big enough as it was. I've barely managed it so far. But I think that's certainly one of the areas of useful future research. And I think having a language that we can actually concretely implement stuff with then makes it more interesting to, oh, now we can, what should we restrict? The other part is, I've taken, of course, I also come from the sort of, dynamically typed world where it's like, we don't care. It'll work itself out. On the other hand, there is a bit of, so for example, I heard some of Herb Sutter's talks on, modernizing C++ recently. And one thing I found very interesting that he said was that, good defaults matter a lot in actually practical safety, not theoretical safety, practical safety. And I think having, so I'm more of a pull and make a good offer to people to, okay, you have good tools, you have a great toolbox that is convenient to use for you to make good architecture. We're not going to do very much to slap you on the wrist if you got it wrong. That can be added, but we want to make it easy for you to make the right thing. Slide downwards to pit of success.
Right. Yeah, I agree with that. We used to say that there was a time when people were trying to design languages to prevent people from making mistakes. And a bunch of us took the other position that was impossible because creative programmers can make mistakes no matter what you do. You're better off trying to design a language in which it is easiest to do the good things, which is what you've just said. So thank you.
Yeah. Thank you very much.
All right. Thank everybody. The conversation can continue, but the session's officially over and lunch is starting. We continue in this room at 1.
I hope you all had a good lunch. I think we can start our second session. Yeah. Welcome back, and also welcome the new faces that did not attend the first session. Is this on? Test, test. Also welcome the new faces that could not attend the first session. So this is the first session with essays. As tradition, those get a little bit more time, so we're looking for about 40 minutes per essay, including discussion. The speakers can decide how much they want to talk, how much they want to discuss, and engage with the audience. And yeah, our first essay, talk, is a case for feminism in programming language design. So, give a hand for Feline. The stage is yours.
Yes, it's muted.
Yes, try to. Am I on now? Yes, I think so. Awesome. Okay. Hello, everyone. My name is Feline Hermans. I'm here to present a case for feminism in programming language design. This is joint work with Ari Schlesinger. Sadly, she's not here, so I hope she's on the live stream. And I want to talk, as I said, about feminism and programming language design. And maybe you're like, what? Like, what does feminism have to do with programming language? These are two worlds that I cannot reconcile. So I thought I will sort of meet you where you are, which I think is knowledgeable about programming languages. So we're going to start with an interactive, is it a programming languages quiz? And this is a super easy quiz. I'll just show you something that is a programming language. And if you think, yeah, that's a programming language, you raise your hand. And if you're like, nah, that's not a programming language, you do not raise your hand. That's the deal. You can also get extra points for guessing the programming language. So we will start with this. What is this? It is C. So is it a programming language? Yeah, so overwhelmingly people are like, yeah, C is a programming language. Okay, what is this? UML, yes. Is UML a programming language? Sort of 30%, I think. So what is this? It's a spreadsheet, yeah. So are formulas in the spreadsheet a programming language? Ah, not bad. Like 80%, I think. So what is this? Scratch, yes. So is Scratch a programming language? Oh, overwhelming majority, yes. Okay, so what is this? It's a knitting pattern. Bam! Yes. Is this a programming language? So there's 60%, I think. Okay, one more. What is this? It is HTML. Is it a programming language? Yeah, okay, so less than half, I would say. Okay, so what we have now established empirically is that there is something like programming language-ness, right? That some things are more or less a programming language, and there's general agreement on what is a programming language, but there's also some differences. Not everyone voted the same all the time. This is sort of what I thought the vote would be, which I think is more or less correct. Like UML is least a programming language, and C is most a programming language, and the rest is somewhere in the middle. And then I'd like to reflect on what is the process that we use to decide this, right? What do you do in your brain if you decide is something a programming language? What are the tools of thought for this? And I think there's generally two ways that people decide is something a programming language, and it's also something like a decision tree. One is it machine executable? So this is something you can do. If a machine can execute it, then probably it's a programming language, and this has nice properties, and Scratch and C are programming languages, and UML is not really a programming language because it cannot directly be executed. So someone will say, yeah. Not directly, easily. So it can. So this is a nice division, but then if you just look at machine executableness, then many things are still a programming language, including HTML, which very often people are like, nah, HTML is not a programming language, so maybe this is not a good division. There's another division that people very often make is it Turing complete, right? And that has good properties because then you get HTML to not be a programming language, which is what you want. And then you get Scratch and C to be a programming language, so yes, this is good. But then you get side effects like Magic the Gathering then also being a programming language, which are probably also not what you want, right? So there is not a decision tree that you can use. There isn't an algorithm to decide if something is or isn't a programming language. And from that we can conclude that what is a programming language is a social construct. It is socially constructed what a programming language is, and this also changes over time. I am old enough to remember when Python, now the leading programming language in the world, wasn't a programming language, because it was a scripting language. And then, like in the 90s, in the early 2000s, that was constructed socially as something different from a programming language. You either were a programming language like C, that had a compiler, or you were a scripting language used by script kiddies. So that even can change, right? And now sort of Python came into the fold of being a programming language. So programming languages are socially constructed, and that means if we want to study them, we have to use technology and tools that is talking about social construction. That is maybe feminism. And this, what is a programming language, for me, isn't an intellectual exercise. It isn't like, oh, I'll sit down in my Chesterfield and smoke a cigar and think, what is a programming language? Oh, so interesting. This is like, it is in my soul, it is in my heart. Because some people might know my research for a long time. When I was doing my PhD, I was working on spreadsheets. And I think I was doing really interesting things, bringing technology from software engineering to spreadsheets, like refactoring tools, unit testing, to help people that build spreadsheets build better spreadsheets. So I was like, hey, hello PL community, here I am, I do something super cool. I work on spreadsheets. And then the programming language community was like, that's not real programming. I was like, whoa, 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 wait, right? It is a functional language, it is reactive, which then was a very cool thing to be a reactive programming language. Like, okay, I get your, I get that you're somewhat comprehensive about this, but look, it has all these features that are like programming languages, and many people can use it. And people are like, yeah, it's not real programming. I was like, wait, okay, no, I got it. I made a Turing machine. Look, I made a Turing machine in spreadsheet format. Now y'all have to be convinced, right? Look, it is Turing complete. And people are like, no, it's still not a real programming language. It doesn't matter, like because it's socially constructed, right? There isn't a proof that you can have. People are just like, no, spreadsheets is for normal people, for no programmers, so it cannot be a programming language. So then after a while, like I got like really depressed. I was like, I don't wanna work on spreadsheets anymore because this is not good, right? And it's so, like, it's super sad. I feel sad for my previous self that I couldn't pursue that line of research, and I just stopped doing that. And I almost stopped doing research entirely, actually. After this, I was somewhat done with academia, and I started to work in a middle school to teach programming to young kids. I thought, well, at least they will be nice to me, and they were. But then, I am a researcher, right? There's nothing I can do. So when I started to teach 7th grade, I saw all those interesting programming questions, and then I started to get warm again about doing research, but research and education. So I was like, okay, well, to get myself out of this depression, I will start to research how do 12-year-olds learn programming. And then I figured out there's a really nice community about computer science education research. And I was like, yeah, Feline, that's awesome. You join our troop. You come to ICER and 60, all those programming education conferences, and you do research there. And like, yeah, this is so fun. I'm entirely alive. I feel better. And I lived happily ever after. The end. No, of course not, right? Because I am a programming languages person. Like, thinking about programming languages is just my thing, and specifically making programming languages so that more people can enjoy programming. Like, I think knowing programming is one of the biggest gifts that you can know, and next to knowing knitting. It is just so good, and I just want more people to have that. So when I saw all those 7th graders struggle so much with programming, I thought, what they need is a new programming language. So in the early 2020s, I created a programming language. It's called Hedy. Who's heard of Hedy, my programming language? Many people. Awesome, thank you. For the people that don't know, Hedy is not so important for this talk, but what Hedy is a simple version of Python that can be localized into different natural languages. So here you see Hedy in Spanish. We support 59 different languages. We also support right-to-left languages like Arabic. This also works. And that was quite an interesting technical endeavor to create a natural language version of different programming languages. So last year I went to SPLASH in Portugal, and I presented a paper about how to make a programming language in different languages, how to localize a programming language. And that wasn't computer science education research anymore. That's true PL work, because we happen to have applied it to education, but you can apply this also to professional languages. So I went to SPLASH last year, and I'm like, hey, I'm back. I swear it's not spreadsheets this time. It is a real language. Like, this cannot be denied. It's like Python, which is a programming language. It's just localized. And what I was ready for is people will be saying, why did you do that, right? Why? And I was like, I feel ready, like I feel ready. You know why? But people said, why is that hard? Why is that hard? And I think this is such an interesting question, because why does it matter whether it's hard? Why is that important? Like, maybe it took me 5 minutes to build this, but many people are enjoying it. When I showed this Arabic screenshot recently to someone from Syria, they were like, wow, I had never thought I would ever see a for loop in my own language. This is just something that touches hearts. So why do people care that it's so hard? But what happened is, you know, I'm a normal person. I just want to fit in. So I entered this conversation. I was like, well, it is really hard. It is super hard. Look at me being a hard programmer, right? Because you have diacritics and word order and regional variants and numerals. It is super hard. Please accept my expertise, right? Be proud of me for doing this work. But while I was in this conversation, I sort of felt my soul leave my body. I was like hovering over myself and thinking, what are you doing, right? Why are you even dignifying this question with a response? Because it is not my value system that things are hard are good. I don't care if it's hard. I care if it makes people happy, and I care if more people learn programming through it. So then I went home, and again, I was sad. I was like, no, well, that was not the success I was hoping for. I don't feel at home in the programming language community. But then time passed, a few months passed, and then I was like, why don't I feel at home in the programming language community? Why? I am a programming language designer. I made a programming language, and I mean, many people make programming languages, but my programming language also has hundreds of thousands of users. So I can say I am a programming language designer, right? This is what I am. So if I don't feel at home in the programming languages community, maybe it's not me, right? Maybe something is there that is just special. So I was like, yeah, I don't feel at home. I don't feel at home. What do I have to do? Help. I have a case of the feelings, right? I don't know what to do. So I could sort of choose two things. It's like one, therapy, or two, science. So I mean, I'm a scientist. So it's like, okay, let me try science first. If you're still all mean to me after this, I will go to therapy, I promise. I was like, okay, so how do you study feelings? How does that work? I have a PhD in software engineering. I don't know how to study feelings. But then if you're a woman of a certain age, then you hang out in women of a certain age circles. So some of my female full professors that I hang out with, they were like, Feline, have you tried feminism? I was like, what? Do you mean feminism? I had no idea how feminism was going to help me, because what I envisioned feminism to be was individual liberties, right? Abortion rights, maternity leaves, women quotas, like the fact that tonight at SPLASH there is a women's dinner, right? That is what I understood feminism to be. And this type of feminism is called liberal feminism, and it sort of says, the world is fine, we just need to pipeline more women into all the systems, and then the problem will be solved. But this was the only type of feminism that I knew, and I thought, well, you know, I didn't need anyone's help to make programming languages, so I don't see how this is going to help. But then what I learned is there's so much more brands of feminism. One specific brand of feminism is called feminist epistemology, which is the knowledge of knowledge. And that type of feminism says, who creates knowledge? Who is involved in creating knowledge? And how does that knowledge get created? Is everyone allowed to participate in knowledge creation? And I thought, this sounds like what I need, right? Because I'm very interested now in how do programming languages get made, and who decides that, and that is knowledge, and how is that decided? So then what happened is I went back into my research diary, and I knew, like, I read something one time about this that might be helpful. And I found this paper. It's a 2016 paper that's called Glaciers, Gender, and Science. And I found this on Twitter, because then Twitter was actually quite fun, where you can learn about all sorts of things that weren't your own research field. And people were actually posting about this paper because they thought it was so silly that feminism would play a role in the study of glaciers, right? Because they were like, well, what does feminism have to, this is like me, right? What does feminism have to do with glaciers? So I'll tell you. There's actually two types of glaciers. I learned this from the paper. One type of glacier is high in the mountains in remote areas. And the other type of glacier is actually low and in rural areas next to where people live. So you could think, like, what type of glaciers would we have more information on? You audience, you may do a vote again. Do you think we have more data on easy to reach rural glaciers? Raise your hand if you think that easy data is oversampled. You see where this is going. So who thinks, yeah, no, the high glaciers, many, yes, but why, right? Why? Because it's harder to do. Why? Because it's harder to do. That is the thing. Because you can gain social status from climbing a high mountain. You can come down from the high mountain, go to the pub, and tell your friends, whoa, I climbed the high mountain today. Like, you can gain social status in that system. Whereas if you gather data where people live, then that is no fun, right? No one cares about that easy to get data. And I was reading this paper, and I was like, wow, so easy doesn't have value, and hard is really valuable. I was like, I learned more from this paper about the programming language community than existing in the programming language community for 2 decades, right? I was like, yes, this is us. This is us. If something is really hard, then you can gain value. You can gain value from proofs. You can gain value from Haskell and C++, but you cannot gain value from Excel or PHP or JavaScript, the easy stuff that everyone uses, right? So finally, I understood the type of pushback that I was getting, because what I'm trying to do with Hattie, and also before with spreadsheets, I'm taking something that is Python and I'm making it easier by making it localized. And I had never understood that there could be any frame of reference in which making something easier isn't good. Because like this is my drive is making stuff easier so that more people can participate. But if this is your frame of thinking, then making something easier is actually detracting value. So I was finally like, I get it, right? If you look at the world like this, then making something easier is bad, is not good. So then I thought, you know what I will do? I will take this entire glaciers paper and look at the whole framework, which is a 4-part framework. Just take this framework and apply it to programming languages to see what else is very similar. Many things are very similar. So this is a quote from the glaciers paper. Natural sciences have historically been defined by, and their credibility built upon, manly attributes. So that is this, right? That is the manly attributes, that doing something very hard is good. And of course, that doesn't mean it's only for men, right? Women can also climb mountains. But that means that the value system rewards something that we typically associate with men, like being strong and being tough. But then this part is hard, right? This is not exactly the programming language community, because historically being defined by, well, wait a minute, our community is not always historically it has been defined by this, because there was a history in which all programmers were women. This is a cosmopolitan from the 1960s that maybe some people have seen before. And here, all programmers were women. And they say stuff like, it's just like planning a dinner. Programming requires patience and an eye for detail. Women are natural at computing. Like, this too is sexism, right? But it is very interesting that at not even so long ago, like some people in the audience might have like been there in the 1960s, that then programming was female and it swapped to being male. So if I say something like a programming language is a social construct, I also mean this, right? Because in the 60s, apparently, a programming language was socially constructed as something that women were good at, and now it is reversed. So there's a lot of research about that early computing was very, very open to women. And this sets it apart from the science of glaciers that has always been male and sort of remains male. Programming had to be made masculine. It was female and it had to be made masculine sort of by force. And one way that it was made masculine is that it was made mathematical. So early programming was all sorts of things, right? It was electrical engineering, it was linguistics, it was cognitive science, and then sort of mathematics came along, took programming in, and made it their own. So one person that was instrumental in this is Dijkstra. So here's a quote from an EWD, which are these blog posts or Twitter posts of la lettre that Dijkstra wrote, and he says, "I intend to present programming as a mathematical activity." And it's interesting, not just that he says this, but when he says this, right? Because apparently, if he says, "I intend to present it," that means it's currently not mathematical, right? If everyone already agrees, you're not writing this, specifically not Dijkstra, because he also always wanted to write what people were not yet thinking. So this means it's not yet mathematical, and he writes this in 1973. So apparently, before it wasn't really mathematical, and this is 20 years after the first compiler and 30 years after the first computer, programming had to be made into math. And then what are his arguments? What does he say? Well, why is programming mathematical? He says, well, an inventive and effective mathematician will find challenge. Challenge! Come here, guys, the glaciers are very high. Come on, much climbing to be done, right? That is the argument. Here, look, it is challenging, so all come here. And of course, it's not like Dijkstra made all the rules by himself, but it's clear to see that in all sorts of ways, and the essay actually describes this in much more detail, programming was made into math and therefore made smaller and much more into these manly characteristics. So what the Glacier paper also says is that most research stems from information by men, about men, with manly characteristics and within masculine discourse. So that is also, yes, that looks like the programming language community, right? Information by men, about men. Here's the history of programming languages, ACM, this big thing, the hop-all that they do sort of every 10 years. The most recent one had 46 authors, of which only 4 were female. And together, the 4 female authors only wrote 2 papers. So 3 were on one paper and 1 was on another paper. So, and this is 2020, right? This is not the 70s. And this just happens, right? And I don't mean to blame one individual person, but apparently we have this system in which this can exist, and no one stops this from happening. And it's not just academia. Here's a book that's called The Masterminds of Programming that talks about different programming languages. And I know quite some people use this book as a sort of an appendix also in the programming languages course, because it really nicely talks about how different programming languages were designed. I mean, it's a really nice book, but it interviews 27 people about 17 different programming languages, and literally all of them are male. So that's like, yeah, you know, that's not great. Like, some people are not included. And it's not even so interesting to only talk about the gender of the people that were interviewed. It's also interesting to look at what is in there, because UML is in there, and SQL is in there, right? And I get why you want to include UML, because Grady Booch is super cool. Like, he's an awesome human being. So I see how here you want to quickly move the goalpost to include UML so you can interview cool people, even though generally, like, we all sort of agree that UML is not so programming languagey. But that we can include because it has a value, whereas I'm like, yeah, but what about spreadsheets? And people are like, nay, not spreadsheets. So it is very much socially constructed, and then we live in a world in which this can just happen, and no one is super upset. So it's not just information by men about men, it's also this manly characteristics within a masculine discourse. And this is, I think, mostly reflected not in what we study, but how we study it. Like, what aspects of programming do we study? I think we can all easily agree that what programming is people put programming code into machines to make the machines do things. So that's like people and computers. But mainly in the PL community, what we study is the computers. We do proofs, we do benchmarking, we build stuff, and like, look, I build a thing. And what we do not really do is observing or interviewing. How do people use the tools that we use? It's sort of like, no, people will figure it out, or they won't. I don't care. It has nothing to do with me. And this, again, also, it is not a coincidence, right? It's not like, oh, just naturally we all grew very interested in computery stuff and we forgot about the humans. Here's another quote by Dijkstra that actually, if I read this quote, it makes me mildly angry. He says, by claiming they can contribute to software engineering, social scientists make themselves even more ridiculous. And then still, like, I have to live in this world, and people are like, oh, Dijkstra. I'm from the Netherlands, and I did my undergrad in Eindhoven, right? So I was like, oh, Dijkstra. I was like, yeah. I know, like, Dijkstra has algorithm. It's very smart, but also there was some problematic stuff there. So we see that still, that the stuff where social scientists could have helped us isn't being studied. So here's an actual paper that exists in the PL community. Like, there's nothing wrong with this paper, right? So it's not something specifically wrong, but what we can study is type systems with for high assurance verification of Rust programs. This is a paper that can exist. Or static information for flow control in Rust. These are papers that can exist. They can flourish. People build a career out of this if it's a POPL or a PLDI paper. But then there's also papers that just cannot exist. Like, the reason I have Rust here, because I think Rust is so cool because people love Rust. Like, somehow people go bananas for Rust in ways that I have not seen people be excited about. I don't know, Java or C. Even Haskell, right? People are like, oh, Rust, I'm a Rust station. They identify as being a Rust program. I think that's very cool, and I would like to know why, right? I would want to know, why do developers love Rust so much? I'm curious about this, but I cannot do this work because where would I publish it? And it's also it's not a social studies thing, right? You need deep programming knowledge to do this work. Like, imagine I would actually do this. It's like, hey, why do you like Rust? And people are like, I really like the borrow checker. So then you have to understand memory management to say, okay, tell me how this differs from a garbage collector, right? So you have to know the lingo of the programming language to really make sense of what people would say. And here's another paper that I would like to do, but cannot exist, like when type systems get in the way. We all know that, yay, type systems, awesome, but sometimes you're like, I know that this works, but the compiler doesn't listen to me, right? Yes, exactly, you all know this. So I would like to sit down next to people, watch over their shoulder when they curse at the compiler and when they curse at the type system, and to tell me what, right? Because this will make programming languages better if I can do this. If I can understand when a type system is harmful, then I can make a better type system. If I can understand why people love Rust so much, I can build better programming languages. But I cannot do these things because you cannot do this research, because where would you publish it, right? And maybe some of you are like, no, Feline, this work can exist. Because one time, 10 years ago, we had one paper at Onward called Socio-PLT. And this is an awesome paper. I love this. And this is a very, very nice paper that has actually looked at how do people adopt programming languages and what are the factors in that. This was a paper in Onward 2012. It even won Most Influential Paper Award. So you're like, oh, awesome. Sociology is cool. Many people will do this. No, many people will not do this. And I actually reached out to Leo Meyrovich for this paper. And I asked him, like, where are you now? And why is it not here? And he said something, it was so heartbreaking. He said, I know if I want to pursue this line of research, I have to have a POPL or a PLDI paper every year because that's how you build a career. And maybe I can do this once, but I cannot do this all the time because it's just a novelty thing. And specifically, he said, if I want to build a career out of this, I have to also do this with students. And I cannot force PhD students to do the soft stuff of PL because it cannot be published, right? You cannot build a career out of this. So he's no longer in academia. And I'm like, see, this is how hard it is. This is what the manly characteristics and the masculine discourse does to us, that some things are included and some things are not. So the Glaciers paper not just looks at the past, it also looks at the future. Like, how do those systems of power stay in place? And then maybe you're like, yes, Feline, let's talk about the future because it will be great. It's like, no, I have some bad news for you because it's really, really hard to change social systems. What the paper argues is that discussions perpetuate certain power dynamics, all sorts of different power dynamics. Once they are in place, they're really, really, really hard to change. For example, the personal dynamic, that I have been in many conversations in conferences around the world where people are like, hey, what did you do? And it's not even like about spreadsheets or anything, but it's about how do I research? It's like, wow, I interviewed a few people and asked them what they thought. And people will say, interviewing is not computer science. right? It's very hard to battle that level. Or people will say, what is qualitative work? What does that mean to do qualitative work? People that are laughing are also doing qualitative work, and they have read this question before, right? And then yes, it's true, thank you. And then you have to explain like the basics of your research methods. And of course, it's not a problem to explain what I'm doing, right? That's why we're at a conference. But imagine that if your research methods are non-traditional, then all your conversations are at this very low level. No, 10 is not a small sample size. No, there is no student t-test in this paper. So you can never really do interesting conversations, whereas the more mainstream you are, the more people have actually deep questions. They're like, oh, but did you read this? So when I was a grad student, all my fellow PhD students were always like, oh, I went to a conference and it was so great, I came back energized. And I was like, well, I came back depleted and sad, and like now I understand why. But it's not just interpersonal dynamics, it's also structural dynamics of power that, of course, in our community is not literally the law, but there are rules and there are also written rules. For example, this is the call for papers of Moldable. So what does this say? How do you get something into Moldable? Well, it has to be fundamentally sound. Okay, that's nice, but what if I want to do this Rust study, right? What if I want to study the principles on which people enjoy programming languages? Right? And it has to contain sufficient information for other people to reproduce the results. But the goal of qualitative work is not to reproduce the results. The goal is to learn something and to build upon that from there. So that is Moldable. I also have PLDI here. So they have in their reviewers guidelines 2 ways that you can look at a paper. You have to make sure that there are appropriate and clear experimental design and that there are relevant metrics. So only quantitative work can get in because I don't have metrics. And then I feel like the PLDI people, they are trolling me, right? Like look at, they have an FAQ. They have an FAQ about their reviewing process. They say, hey, but what about human factors? I'm like, I would very much like to know what about human factors, you friends? No, sometimes PL involves user studies. However, those are currently relatively infrequent in the papers we examine. And why would that be? Right? So it's not even that they don't know. Like they know there's an issue, but yes, I don't know. I don't know why there aren't any people here. So these dynamics, they perpetuate power through the centrality of math and technology. And you see that also with Moldable and PLDI, metrics, reproducibility, it narrows what you can do. And then of course that doesn't mean that you can never get anything else in, but it will be a lot harder to sustain a career on that type of work. So that is an overview of what is in the paper. There's much more in the paper in a lot of painstaking detail. But I want to sort of close it with, now what, right? What do we do now as a community? So I also don't know. I don't know. But as I was researching this paper, I felt so, like my heart was warmed sometimes. I was reading so much work on female programmers. There were so many researchers, male and female and other, that have researched how women feel in programming. And there's this one quote from one paper that I want to share, because it said, women can be coders or female, but not both. This is how people feel, right? This was an interview study in which female programmers were interviewed, and they felt, well, I cannot have my female identity. And I read this, it's like, this is me when I was younger. Like now I'm here in a skirt and hoop earrings. But definitely, and I'm knitting in sessions. But I wouldn't have done that 10, 15 years ago because I didn't want to bring even more attention to my gender. I thought if I just have jeans and a t-shirt, no one will notice, right? So, and I know that won't work, but this is how I felt, and I didn't have the words. I'm reading all of that work, sort of made me feel so seen, and that was good and nice. And I was thinking of this James Baldwin quote that says, you think your pain is unique, and then you read. I thought, that was me. So I was happy, but I was also sad. Sometimes my heart was also just cold, because I thought, why am I doing this work, right? Nothing uniquely qualifies me from doing all this work. Anyone in the community could have done this work. I'm already marginalized by being female and also doing all the qualitative soft stuff. Why do I also have to, for half a year, I wasn't working on my actual research agenda, I was working on this. So why do I have to do this, right? I would very much like to live in a world in which much more students had one course about critical theory in their undergrad, right? How is it that we don't live in a world in which computer science students or all technology students learn that, hey, you're building technology and all technology is socially constructed, also compilers and operating systems. And you have to talk about who is building this and why. I would like to live in this world, but I don't. Even more so, I live in the opposite world in which computer science programs and other technology programs tell students technology is neutral, right? This is math, so there's no people-y stuff involved. And then you have to keep doing this. So I was also sad, like, I would just like to build compilers, right? I don't want to do all this stuff. Why do I have to do this? But I don't know, therapy is expensive. So something else that I want to talk about is we talk a lot, if we talk about diversity and inclusion, about bringing more women in. And that is good, right? I love it that there's a women's dinner tonight. That is really good. However, we also have to talk about what happens with women when they're in the system. If we pipe more women into this hardest valuable stuff, then this is the only way that you can think. And for some people, that might just be a hat or a way of thinking that fits really good. But there's also a lot of women and also men that don't want to think in this way. And it's just very sad if we lose them. So if we want to get more diversity in all sorts of ways, then we cannot not examine the culture that we have, because a culture encourages some people to participate in some ways and discourages others. So we should sort of not only focus on getting more people in, we should also focus on changing the system. And I don't know how to do that, but probably some call for papers explicitly soliciting more qualitative work and explicitly finding reviewers that can review it. I think that is the way to go. So something that I would really, really like to exist is that gap that we have here, right? You have software engineering and HCI where some more qualitative work can exist. It can also exist in computer science education, but it now cannot exist in PL. So those studies about what makes people tick, what makes them enjoy, or what makes them hate a compiler, this work is not just not here, it is nowhere, right? We don't know, as a humanity, we don't know why people like a certain programming language. And we all know this. We know that there are certain things, but we don't have any theoretical frameworks for programming language understanding or adoption. And this is just a loss, right? So if we could just have a little bit more human studies into PL use, not instead of what we're doing now, but just in addition to what we're doing now, and not just on the fringes, right? People say, yeah, Eveline, but there's plateau and life. Yeah, but we all know you can't sustain a career on those workshops, right? It needs to be in the high-profile top venues, or it is not sustainable. The end.
We do have time for some questions.
I was going to say bonjour, but I can't remember what the French for good afternoon is. Mais je comprends pas. Non, je comprends la raison pour le choix de la langue de programmation. C'est la langue que les programmeurs comprennent, n'est-ce pas? Sorry, that's a cynical introduction.
You don't understand.
I don't think it's as bad as you think it is.
That is not a question.
I'm mostly going to advertise stuff, I think you do know what we need to do, and I think, frankly, we know what we need to do.
Okay.
Really, as I said, this isn't a question; it's an ad. So there has been a stream of, I'm tempted to say, feminist influence work that's been published at ICSI. In particular, there was work by Angela Martin, which I have a little handle in, which famously found out that the customers in Agile projects were working 80 hours a week, while all the male, and they happened to be women, while the programmers were working 40 hours a week. And more recently, there has been some stuff on choice of, things like choice of software architecture. Why do people choose a particular platform? And recently, and this is a blatant plug, there is a book just out this month published by Springer called Socio-Technical Grounded Theory by Rashina Hoda, who has just made full professor at Monash, who I'm very proud of. So I think one of the things that we can all do is, read that stuff.
Yes.
And cite that stuff.
Yes. So absolutely, and I think this was my previous slide that I was thinking on. The situation in software engineering and other fields in terms of qualitative work is much different, but I think it must also at least exist a little bit in PL.
Sure, because I mean, I think that's why I started speaking in French, because I think there are all kinds of questions that cannot be answered unless you take this at the very least more, where you start thinking about the people rather than the languages. That's different from studying languages and using people as a research instrument. I mean, the question I would love to answer is why. I really shouldn't do this, but I'm going to do it anyway. I'm sorry. It was an interesting and very thought-provoking talk. I would love the answer to this question. Why did Haskell get away for 20 years with no static checks for a coverage of a pattern match at exactly the same time as the functional programmers were damning Java and every single object-oriented language because Smalltalk had a message not understood error, which is a non-coverage pattern match.
But these are the type of questions that
you can't do that, and you haven't been able to do that
But
in Java
I would now
ever.
very much like to hear some actual questions. So if we can move on.
Thank you. Thank you. The line is very long. We still have some time. Yeah, go ahead.
Okay. Thank you very much for the talk. It was really something I didn't expect, that you actually took something more than liberal feminism and applied it to computer science. But I really wanted to ask you, if we introduce more social sciences into our research, wouldn't we also replicate just the masculinity in social sciences? Because I knew some social science, and it's just like the same thing replicated, maybe a little more like qualitative research, but it's still very manly in a sense.
Yes, so this is a great question, right? So all sorts of science suffer from these problems, some fields more or less. But I know also in sociology, quantitative work has a higher status than qualitative work. So we have to make sure that if we import that, then we do it in the right way. But whatever way we do it, we have to also look at people, right? So I don't know the best way, because that's not even my field. As I said, I'm just a simple programmer. But however way we do it, we have to include this human perspective, and that will bring more diversity in the people that do it, and also more diversity in the things that we do. But you are right, we have to do it in a careful way.
Yeah, thank you.
First of all, a little bit of validation. I really appreciate your call to action for making more qualitative work in our field. We've dipped our toe in the water several times, and the papers get accepted on the 3rd or 4th iteration. So we'll see about our interview study for Russ. That's on the 3rd try right now.
Yes!
Maybe we need venues for this, I don't know. But my question was actually about a comment you made, and I apologize for my great academic grandfather, Dijkstra, who, but you know, I wonder if you have thoughts on why math itself is coded in such a male way.
Yeah, that is a great question. So a little bit, there's some of that in the paper. I think, I'm not even sure if math necessarily is coded in a male way. It's more that the things we associated with men are more likely to stick, right? There's so much math in knitting and in quilting, but that part is also math, right? Have you ever made a complicated sweater? But then that math is not in the normal math, right? So what is the normal math? The normal math is also separated, divorced from people, right? It's always about algebra and abstract things. So if you're a person that likes people, and women are more likely to be interested in people, and we don't know if that is nature or nurture, but it doesn't even matter. So I would not even say math is so much male as math and other things are divorced from people, and that just impacts who wants to participate, who's excited about participating.
Hi, this is really cool. At I think it was Popple last year, there was this conference on the future of programming languages, and one of the panel members was suggesting that the reviews get, or the call for papers, like you're suggesting, get expanded, and we start incorporating more crazy ideas rather than being sort of in the dead stayed like paths. And the response from the other members in the committee was, well, we don't want Popple to lose its rigor. And
that can go in my next version.
Yeah, right. So I was just wondering, like, how do I, as a young researcher, have conversations with people who are on these kinds of panels? Like, how do we start to have conversations with people who have the power in these?
Like, I don't know. I'm sorry that you had to go through that, right? So like one thing is I did a little work on this paper, so this is something you can share that maybe helps, but also if this culture is the way it is very hard to change, right? And in order for you to be in the steering committee of these conferences, you have to be well established in the current way of doing things. So it's really, really hard. So I think the best that maybe we can try for is at SPLASH, there is SPLASH', which is a track about education, but it's in SPLASH. So maybe if it is a separate track, then at least the people are there and you have a group of people. So not a workshop, because a workshop sort of has a different status. But that is something that maybe you can make a safe space of qualitative people that is there but not there. But people that say, well, it will lose its rigor, right? This, I think, is very unlikely that we can change the minds of enough of those people to really change the field. So you have to make a space that has both the prestige and the safety somewhere. That's probably the best we can do. But like my concrete advice was, let's not do workshops because it is not enough of a status gainer.
Thank you.
I think we can take the two last questions, but we can switch laptops already.
Yeah.
Go ahead.
Okay, thank you for the talk. I think these are really important issues to talk about. I'm wondering what the next steps are in terms of like what to actually do about it, right? And so, so one direction that I'm wondering about, and I'm wondering what your reaction is basically, if you want to show that something has value, then maybe try to have impact, right? And so the first people to do that are going to have a hard time, right? So the neural nets people work for decades and decades, and not having much impact as far as most of us know, and then all of a sudden, boom, right? And so I wonder what okay, it's questionable, right? But it's out there.
Yeah.
And so my question is, what can we do to show that these methods have impact?
Yeah, so I think it's really hard in the frame that we have, right? Because impact almost always means doing something that is relatively easy, right? Like getting people to adopt your stuff isn't hard technical work. So if you have something that is well used, then maybe that is even a proof that it is too easy, right? Because it should be harder. So I don't know if this is the way to go. I don't know if this is the way to go, right? Because then you have to show that you're doing this, you have to show that it's still rigorous, but also it has many people, which has a sort of tension. Like there's this great feminist thinker that says, Audre Lorde says, you cannot destroy the master's house with the master's tools. So if you go in this framework, you can never win. You have to do your own thing. That is something different, where you have a different value system. Because just saying, well, I mean, people look at my language and it's like, oh, it's for kids, right? Oh, it's natural language programming. It doesn't matter if many people use it, because it's a different bean counting.
Thank you.
So last quick question.
Quick question. So I thank you for that, and I think I'm in violent agreement with you. And I've been having these rants with many other people for like 20 years now in the hallways of these conferences, and in reaction to that, we've done some things. Like, for instance, you're speaking here at Onward, and Onward is very much a response to many of these issues. And Onward now is a conference in the ACM. I mean, your paper will get a DOI and be published in the ACM DL. And now we have the Programming Journal, which is a similar kind of community that is a real journal that is very much open to discuss a lot of these issues. So we've been slowly trying to infiltrate to fix these problems. And I just wanted to ask you if what we're doing doesn't seem good enough. What are we not? How is Onward and programming not yet good enough for you?
Yes. So I think this is actually a great question, right? Because it's really, really good that those things exist. This is awesome. But as you say yourself, the progress is somewhat slow. And to make it personal and go back to what I was saying in the beginning, the existence of these things has not protected me from sort of not feeling at home. And in every conference that I go to, every time having to defend the topic that I research, having to defend the ways that I do it. So however much I appreciate the things that you're doing, there has to also something to be changed. That if I'm in a conversation and someone says, oh, but this literally happened to me when I was a grad student. A full professor, when I was still a grad student and he was also male, said just in a room like this, oh, but this is not really computer science. And no one said anything. So as long as we're there.
We have to organize them and work together because divide it, we fall.
Oh yeah, no, I agree with that.
Let's thank the speaker again. Yeah, we need to switch microphones. Recharge this one, I think. So this brings us to the second essay in the session. Yeah, and as I thought, luckily we have some extra time in these sessions, so we need it for that one. Maybe we need it again. And I'm really happy that we can have these discussions here. We should continue in the hallway, of course.
Is this thing on?
Yeah, this sounds,
all right.
sounds good. So, next essay is on dialogues on natural code. Go ahead.
Hello. Hi. That was an absolutely incredible talk. And so I'm feeling the pressure. But I'm also just like hugely honored to follow like, a talk like that. Like you could, I'm shaking a bit. Like I feel the adrenaline. But let's do it. Right. So my name is Lou, or Luke. It's a very long story. And unfortunately, so my co-conspirator Dave Ackley can't make it in person today, but he's going to be involved, and he's also, I think, on the he's in the live chat, I think, on YouTube. And I should say that this work is supported by his not-for-profit called Living Computation Foundation. Paid for my ticket today, so I just want to give thanks to anyone who's ever sort of contributed to that. If this is bad, then it's your fault. Right, so to give you some background, that's me. For a long time, I was a teacher for like most of my career. I was a teacher. I worked with really, really tiny kids, mostly, but not always with. Look, I'm shaking. I'm shaking. Oh my God. Okay, mostly, but not always with communication difficulties. But currently, I'm a software engineer at TL Draw. I'm also a researcher in residence at a lab called Ink and Switch. And I'm part of this new collective called Tentpole. But yeah, anyway, part one, Lou, that's me. So to explain this piece of work I'm showing today, I need to go eight years back to when I was a teacher, right? So that's me. That was before hormones, right? So, and when I was a teacher, I discovered these videos on YouTube by Dave Ackley. He has this whole sort of, this body of work on the internet for everyone to see. And the reason I watch them is because he has a very relaxing voice. And I'm not joking. That is why I watch them. I really enjoyed how calming they were. They're kind of amazing. The setup is fantastic. It has this sort of like black background, and Dave like looks through his slides to the left, often wearing a suit and tie, not here. But after watching this video for about like 100 times, some of its ideas started to resonate with me, right? So this is Dave showing the simulation of artificial life, right? But Dave said it was more than just that. It's more than that. This is not just artificial life. This is life, right? And I thought that was interesting. That was interesting. So I started to build my own things, which were similar. And this was the first thing I ever made, sort of inspired by Dave Ackley's work. And I sort of kept going, and I haven't stopped. And so I made this thing called Sand Pond, which is like a living computation. It's a simulation. And yeah, and I've kept going. This is like my latest attempt, which I presented last year at Splash, at Live. And it was the first time I've presented anything like academic-y in my life. I was inspired in other ways. This is another video he did. This on the left here, that's called the self-image. It's his symbol I'll get to later. And I sort of ran with that icon, like that symbolism in some of my more artistic projects too. So, okay, so yeah, I was sort of deeply inspired by Dave Ackley's work. And one day I put out this blog post on my blog. And on my blog, I usually write things that I've like learned or I'm trying to sort of reaffirm to myself. And one of the things that I did learn was sometimes you can just ask questions, right? I don't know if you know this. You can just ask for things. And I guess Dave read my blog post, so he sent me an email saying, just asking, this was immediately after the blog post, would you be interested in booking a Zoom slot sometime? Like, I've noticed you're obsessed with me, Lou. So we had a Zoom call, and it was like shortly after my birthday. And it was great, and we carried on chatting about once a month. I learned a lot from him about like working in academia for a long time, publishing lots of things, like how he thinks about code and what it means for something to be anyway. And then he said something crazy, right? He said something crazy. He said, let's write a paper. And I said, well, that's ridiculous, that's ridiculous. And actually, we didn't write a paper, we wrote an essay. And I'm very sorry, Jonathan, because I read your call for papers, and we wrote an essay called Dialogues on Natural Code. Right? So one of the things that we were talking a lot about at the time was okay, so Dave has this crazy idea, right? And I say crazy as a compliment, right? And so I asked him, so why is it so important to you that we see natural language as code? Because this is something that Dave kept saying to me, right? He kept saying that all communication can be viewed as code, right? All of it. All of it. It's this crazy idea. And this idea is called, there's like a delay, natural code. Right. I'm going to like work that into my timings, right? This idea is called natural code. You know, kind of like we have programming languages, right? And we also have natural languages, so we can also have like natural code. It's a cutesy name, but that's what it means, right? And so we thought like the best way that we could do our essay was to actually make it this dialogue between me and him to be like this example of communication, this example of natural code. So what we did is we recorded all of our calls. We had like a call a week for many, many, many months, and we recorded everything. And then in the essay, it's just snippets of that. Right, so including the bits where we interrupt each other, especially those bits. It's often the most interesting bits. But I would say that there is some cleaning up, right? It's not completely faithful. Like, and trust me, like this is what I actually said, and this is how much better it looks in the essay. So you're welcome. You don't want the truth. You can't deal with it, right? The other thing we did was like the nice thing is you can add references to something you've said. So sometimes I would say to Dave, it's like, oh, but trust me, I can reference that, when I've got it in the back of my mind. The other thing you can do is refer to Fig 2 in your essay. But actually, like after doing this for many, many months, and we got conditionally accepted, so we actually spent a lot more time on it as well. We got quite used to this format, and many of the dialogues actually started happening like async. So this particular paragraph, I wrote that top line on one day. One day later, Dave wrote the second line. A day later, I spoke on the following one. A day later, Dave wrote on the following one. So these dialogues weren't just happening at the same time. They started happening like in many different ways. And yeah, anyway, back to the talk. So, to answer this question about like why
why Dave has this idea of natural code. We figured out through this whole dialogue that it starts with this, right? It starts with this. Dave says, I think living organisms can be meaningfully viewed as machines. And that's the first line of our essay. And of course, my response is it's just, sorry, what? You know, like animals? Like, when I think of a machine, I think of like a computer or like a gizmo or a gadget or a robot. But no, Dave says machines are physical arrangements of matter. They move and do work. And they have power supplies, right? And you know what that means, right? You know what that means, right? Like, does that mean we're machines? You know, I don't feel like a machine, right? Am I a machine, right? Am I a robot? You're nodding. The thing is, I'm not this kind of machine, right? I'm this kind of machine, right? I have power supplies. I have power supplies with the food I eat and things like that. I'm an arrangement of matter. The thing is, when I go to the doctor, I kind of want them to think of me as a machine, you know? When something's gone wrong, like, you know, my immune system's all messed up, right? I need them to think about me in terms of like matter and biology and bits and pieces, right? So this is the first idea, right? We are machines. Following so far? Yeah, you're just going to go with me, right? You're going to go with me on this, right? So as well as being machinery, living things are also capable of building machinery. That's what you're saying, right, Dave? That's what you're saying. You know, like, we build bridges, they're machines. We build programmable machines, like Turing machines. You know, and Dave was saying that, no, it's even more than that. Like, even a fire, even a campfire, we still have to build, right? Like, we get bits of wood, we build this campfire, and then we like push its button, we flick a switch by lighting it to turn it on. So one example we used in the essay was burgers, right? Dave was saying to me that even building a burger is like building a machine, right? It's a really bad example. But like, and one of the reviewers really disagreed, and I would like to thank our shepherd, Alan, for discouraging us from writing a whole page on the machine status of the burger, right? Maybe next year, right? But the thing is, if we're machines as well, like another way that life builds machinery is through reproduction, right? That's pretty, like if we really accept those first two things, you know, we are machines, we build machines, right? And I said, you know, Dave, and you're saying, just want to get this completely right, there are two ways of building machinery, right? Directly, you know, with wood, hammer, nail, we build a machine with our hands and tools. But also, indirectly, you know, you get another machine to build a machine for you, right? If you can find a programmable machine like a robot, you can ship some code to it and get it to build a machine for you. Or we can transmit code to that programmable machine. Or even just like flicking the light switch on the wall, we can kind of see it. Like, if we stretch our imagination a little bit, we are like programming it in a way. It's just a very simple program. And these are some mantras that Dave kept saying to me. We ship code, right? We are coders. We could say. So, catch up. We are machines. We build machines. We program machines. This is all pretty normal, and now it's going to start to go really crazy, right? Okay. So. I said to him, okay, I see where this is going. So you're saying that the programmable machine could be a person, right? You could, like, if we accept those three things, then we could say that we code a person. And Dave says, yes, we transmit natural code all the time. When we talk with each other or teach stuff to our kids, you know, we could say to someone, hey, can you help me build this shelter? In a way, you're transmitting code to them. You're trying to get them to do something. You know, can you build a fire while I gather food? Or even something like duck, there's a rock coming. You know, it's a way, you're trying to help them by coding them. We are machines, we build machines, we program machines, we are programmable. This is the crazy idea. Sometimes we're the coder. We already know we're coders. We're all coders here, right? Programmers, sorry. But sometimes we're the machine. We're the machine, right? This is the crazy idea of natural code. And Dave says, if I was trying to wrap it up, all up in a box, I'd say, and we did, I think we should use, yeah, I think it's nice when you can format your speech, you know? All right, I think we should use our knowledge of programming languages, of software and computing to examine our own natural code, to understand it and debug it, to make society better and to improve our shared code base. Natural code is like another lens we can look through. It's not the only lens, it's just another lens. Warning! Warning, warning, warning. This is a technological fallacy, potentially, right? So reviewer C put it really well. They said, you know, they're worried about the ideological, technocratic undertones of the essay. It's a pervasive fallacy in the tech world to see all our problems as technological, right? Every human interaction, I'm saying, is reduced to a kind of programming. And I completely agree. And this was something that we were really worried about. And I think this is like a risky idea, because if people take it in the wrong way, it can be this sort of like this imposing of tech on everything, which would be terrible, right? And so I think it goes even further. I think it almost seems like psychopathic, right, to say that like we're coding people, we're trying to program and manipulate people, right? And Dave, I think he was a bit shocked by this, right? But like, I think it's really important that we see it from a different point of view. That's not what we're saying. That's not what I'm saying, right? I think we're very used to coding other people. We have a code of conduct, right? Already, we all do this already. You know, like we've all been coded by one of these things, right? You know, design systems a computer is not consuming this. It's a person that's getting coded by this. A pattern language, like it's a way of coding people, right? Advertising, you know, that's a way of manipulating people, but we should at least, why not just acknowledge that this is trying to program people to drink Coca-Cola? Actually, I had one for lunch. All right, so, did I get programmed by my own slides? Oh, this is not subliminal. So, like, I think this is important, right? You know, like, we need to be careful. There is the potential for a technocratic fallacy, right? We can't boil down communication to just getting someone to do stuff, because that's cold, right? But just wanted to give that warning, and now we can continue with the essay, right? So when I was a teacher, like I said, I worked with children with communication difficulties, and a lot of the time, not all the children, but some of them actually struggled to see the purpose of communication. Many of us learn this naturally, many of us don't. And so this is PEX, it's a picture exchange communication system, and it's one way of demonstrating to children and adults that communication is valuable because it can make people do things. So if you say, if you hand someone these cards, I want bubbles, and this happened many times, then I would give a child bubbles, right? And in the paper we talk about biscuits, but Dave keeps saying cookies, but either way. So you know, so many children realize that communication is valuable because when you transmit code, when you communicate, you can get people to do things. And there are ways of sort of building on this, and you can use PEX for much more complicated communications, right? But here's the thing, like, PEX is useful because it uses symbols. Right? If you don't have language, you just have to point or grab a cookie, right? But when you can use a symbol, you don't need to see the cookie biscuit to ask for it. You can ask for it in another room. You can be playing with your bubbles and ask for a biscuit. This is one of the reasons why language is great. You know, like, you can point at 3 cookies if you want 3 cookies. Or you could sort of hand over 3 cards, and then the thing is, this starts to get very cumbersome and annoying, and you know, this is when you typically, if you're a child going through PECs, then you will switch to more advanced abstract ways of communicating. Usually PECs gets very annoying, so you switch to something like a pod book, or just speech or signing, right? But I think this is like an interesting example, because we're acknowledging that communication is helpful because it gets people to do things, right? We've just had to go through it explicitly here. So like a lot of this work is very inspired by my teaching days, right? Of course, it didn't take long for people to, you know, ask for, Mr. Wilson, I want 1 million cookies. No, right? Another warning. This is my favorite one, right? Non-determinism detected, right? Computers are deterministic and humans are not, right, is what I said, right, to Dave, right? How can we talk about code when it's not going to run the same way each time, right? Dave said people certainly, you know, don't do the same thing every time. Many people say, well, if it's not deterministic, then it's not computation. And I have news for you, buddy, right? Determinism is an illusion in the real world, right? All code runs in the real world. I'm sorry to break it to you. Don't shoot the messenger, right? Theoretically, code runs, you know, I don't know where, in PDFs or something, right? But all real code runs in the real world. All running code is non-deterministic. And I can prove it to you. If you think you have found a deterministic program, then bring it to me, and I can prove to you that it will not necessarily finish. All I need to prove it to you is a hammer, and I can smash your computer because it's in the real world. Anyway. The way we get around non-deterministic execution of code is that we can run it again and again and again if we think like the net gain is positive, right? We do this in web development all the time. We do retries, right? So this is how we get around non-deterministic code, is you run it again and again and again and again and again. And now we get to part 2. In that spirit, Dave is now going to tell you some of these things again.
Hey, Onward essay folks.
Could I ask for the volume to go up a bit, please?
Hey, Onward essay folks. I wish I could be there with you, but I am coming to you from last week in New Mexico. The idea here is that I'm just going to try to drill a little bit more deeply into these ideas of natural code for a couple of minutes and maybe find a few takes on them, and then hopefully, Lou will be able to make sense out of it for all of us. So, that sounds good to me as far as it goes. So, the very idea, this crazy idea that saying natural language between people is like code, programming code between a programmer and a programmable machine. I think it's fair to say, as the intro, that both people and both humans, both you and I, and digital computers can be viewed not just as machines, but as programmable machines. Okay, that's great. But in almost every way beyond that, programmable machines of our kind and programmable machines of the silicon kind are almost complementary rather than identical. And one of the biggest ways that we differ is the idea of deterministic execution. That the backbone of traditional digital computing has been this idea of deterministic execution. The hardware guarantees, with an asterisk, that it'll do the same thing every time. And people don't have that kind of guarantee. Beyond just people, living systems don't have that kind of guarantee. The vagaries of the natural world means you have a plan that you're going to try to reach the apple and eat it. But as Professor Tyson once said, everybody has a plan until they get punched in the mouth. That's what non-determinism is like. And what does that mean? Well, that means if we want to think about what's supposed to happen, we have a desire, we have expressed it in code, we want to execute that code or ship that code someplace else and have it be executed there, whatever it is, we have to consider not just the plan as we have stated, the master plan, but we have to consider the possibility that it won't work. We have to consider the possibility that it will fail. We have to consider the possibility that it will work differently on machine A and machine B. Why? Because there are implementation dependencies. And in traditional computing, in traditional programming languages, implementation dependencies are always lame. We hate implementation dependencies as programmers. We want the world, we want the digital system.
Work in web development, right? Like, and when something works different in Safari compared to Fire,
to clean all that up so that it's guaranteed to work the same way every time. That was the deal. And now you tell me it's going to do, it might be signed and it might be unsigned depending on what computer it happens to be running on. Well, I don't want to have to worry about that. Well, the real world living systems have to worry about that. And so once we get beyond determinism, and determinism is like crack. It really is a drug. It really is addictive because it allows us to skip a tremendous amount of stuff about error correcting and deciding whether we would rather have this kind of implementation problem or that kind of implementation problem. It allows us to sweep it all under the rug. That's hardware's job. Hardware provides reliability. Software provides desirability. And once we get past that, once we have to give that up, and I say we have to give it up, that's kind of why we're all here talking. Implementability becomes a primary concern. So we can take this program and we can claim, is it implementable? Can we run it on machinery that we can actually acquire? And it might be possible that the program is completely implementable in some principle, but it would cost far too many trillions of dollars to build a machine that would do it. Or it might be that it's not implementable even in principle because it has some internal contradiction where at one point it's going to say the thing has to be up and the other place is going to say have to be down. Can't be both at the same time. So that's a bummer, but we're going to have to get past that. And if we can get past that, we are going to learn that natural code has all of these techniques, all of these designs, all of this stuff. People have all of these designs and things to help make programmability possible without hardware determinism. So,
like, I love these videos, honestly. Like, I was pleased to get like a custom-made Dave Ackley video, right? For anyway, there's more.
Once Shannon information, send how much information can you send through a channel? Beautiful mathematical implementation, beautiful information theory, mathematics, and so forth. Well understood. Has one huge assumption built into it, which is that the transmitter and the receiver share the identical dictionary. Well, that's great, and it makes sense from the point of view of the phone company. They don't care what language you speak as long as you're talking and so forth and paying a toll. But for a bigger picture, for understanding machinery in general, for understanding how to build entire systems, not just communication channels, we have to understand how does a shared dictionary come to be. And the idea is that Chomsky's hierarchy with recursive modular languages and subclauses and the man with the dog with the hat with the fun and so forth. As a way to get complexity, well, that's great as far as it goes. But we have taken an alternate approach. We say we don't need incredibly complex recursive syntax if we can keep naming things. If we can say, well, A is B, or A is B and C put together, whatever it is, with very little syntax, we can start building a large dictionary and express many, many concepts. And most, I don't know, if we look at the code transmissions that are happening on Earth, if we could imagine analyzing, like the NSA, every bit that moves through every fiber and every radio wave that moves through every Wi-Fi, if we could imagine categorizing all of those computations, all of those code transmissions, a vast majority of them would turn out to be dictionary maintenance, saying A is B, A is B, B is C, and so forth. How do I know this? Because advertising is dictionary maintenance. Advertising is repeating over and over again from the valley of the
Green Giant, right?
There's tremendous.
So I think Dave was referencing, right? I had to look this up, right? Does anyone here know, like, from the valley? Right. So I'm too young.
advertising in the world. Advertising threatens to choke the communication channels that we're trying to send other kinds of code, other dictionary entries that might be more important but less money involved than advertising. And We Are Coders is an example of a advertisement, a slogan, a symbol. Natural code, when Lou and I were having our discussions, didn't start out as natural code. It started out as, what the heck could we write a paper about? And say, well, how about natural language is kind of like programming language. It's like natural language and programming language, natural programming language, natural programming, natural code. And
right, so this is what happened, right? So me and Dave are talking all the time, and I say, that thing you said about how all language is code, right? And he would say, no, it's not quite like that, And then we have to sort of hash out this definition again of like the intricacies of what it means, and it just became so much easier. Should we just come up with a name for it? So it ended up being natural code, right?
That was a process of bumming down a program, making the program shorter, in order to make it more memorable so that we would have a nice little token that we could hang it on. That's why we settled on natural code. We Are Coders is something I came up with a few years ago before. There's a YouTube video about it. It's the same thing. I mean, when I started out, I was talking about we are programmers. I didn't like the word coders. Coders sounded, humble or not as professional, or we are programmers. But the vastly shorter length of coders completely overwhelmed. We are programmers. That is not a slogan. That is not a good tag, punchy symbol. We are coders. It is.
Right. Next. So like there's this live programming. Do you know that there was this thing called live programming, and there was a mailing list for it a long time ago, and it was too long. It wasn't wordy enough. So they changed it to live coding, but it's been very confusing because now there's a new thing called live programming, which is, anyway, it's the same thing with natural code. It was just so much easier and quicker to say it.
Beyond just building vocabulary, we also need to build simple constructs, simple syntactic fill-in-the-blank, role-filling sorts of things, like an API, an application programming interface, in traditional programming. We have this thing, you can insert at the front, you can insert at the back, you can remove from the front or the back, you can ask if it's empty, you can say, these various things, and an application programming interface. And we're going to do the same thing in natural code, but it's going to be obviously not built for deterministic things and so forth. And so I have tried to get myself, instead of saying APIs, which risks the confusion with traditional interpretations, I'm calling them APIs. I'm pronouncing it as a word. And we're making that that's a term of art. That's a jargon term for natural code. An API is a simple template for structuring code, where you can fill in the blanks inside the template and get stuff that might be useful, that somebody might want to explain. And the example that we do in the paper is the idea of the self-image API. And the idea is, and again, this goes from that video about We Are Coders, that if we choose to say, among all the possible processes, the combination of an input, internal sequencing, some judgment about good and bad, and output is a set of processes that kind of all hang together that we can imagine using in lots of ways. So there's a symbol for it. You can see an input side, an output side, a sequence going around in a circle, which I can never get right, and then up and down for judgment and so forth. And they have all these places that we can use them. And so the idea is that something like this figure that we're looking at here, is an API, because it suggests a way of describing many different situations. And, there's a second figure which gives a bunch of examples of all the things that can be put into this same framework and then be expressed using the same API. And the claim is that is useful in and of itself, especially if we can imagine that we're doing it in a way that has room for lots of expressiveness. And so the suggestion is there are states of people that are maybe not optimally desirable, like being depressed, where, whatever it is, you're going around and around, thinking about things in your head, hating it, and that's a bummer. But maybe if we could understand it as part of a more general process of running a search process, process in our heads where we try all these things and that doesn't look good enough, that doesn't look good enough, and so on, and they're just all failing, then maybe actually being depressed is not such a bad thing. Maybe being depressed is we're doing a good job at running our parametric search, but the search is too hard, and so forth. So my feeling is, I've gone past my time, that the idea of natural code is compelling. It's not amazing. It's not a magical, theoretical framework that does anything. It's a way of speaking that has certain useful properties that we couldn't really talk about it this way until we understood programming and digital computing and programming language design to the level that we kind of understand it now. To me, it seems like the early days of design patterns, that there is low-hanging fruit all over the place here, where we could start fleshing out natural code APIs, natural code APIs, and exchange them with each other and say, this is compatible with that, these things go together. We could build a natural code framework that will have more and more and more scope. And that could be good for our computation as a society altogether. Ooh, save me.
Okay. I'm already over time. So I'm going to race through and maybe cut some stuff. But so yeah, this is the self-image that I showed you earlier. This is like just a way of thinking about a computation, whether that's like an unnatural computation like a computer program, or a natural computation like a computer program, right? And Dave gets it. I used it too, but we were kind of both doing this on our own. We were both doing it on our own and just using it for like introspection or something, and that's not very helpful, right? So the whole idea of our dialogues was that we wanted to like sync up, right? Are we talking about the same thing? What are we talking about? And throughout this whole process, I think me and Dave ended up finding some shared language around it, and that's like kind of the output of this work is this word natural code. We know what we're talking about now. There are some things I'm going to skip over now. Come speak to me afterwards. Speak to me afterwards. Do you know what? Actually, I think it makes it better if I just go through the slides like this. We don't need any syntax, right?
Is that syntax?
That's next year, right? Do you know what? This is a way better way of doing a presentation. What I will end on, this is because this is the important stuff. The other stuff was just bonus. Is that, yeah, like I said, this process of these dialogues between me and Dave, it was about building APIs, or to be more specific, building one API between me and Dave, right? For me, it's building bridges, and that's what this natural code idea is about to me. It's about knowing that we're maybe sometimes speaking different languages, and we want to know how to translate between those, right? It's a very general, like high-level idea. I don't think we cut vagueness as a service from the essay. It was in one of the versions. It's been this crazy, exciting experience. Me and Dave, like I'm essentially the second natural coder. Next, I think I'm interested in sharing this more widely and seeing how people react. I have no idea how they're going to react to this crazy idea. We're going to go step by step. That's the end. Thank you very much.
Thank you very much for the talk. There's time for questions. Please line up.
So tall. Yeah. Excellent
Try
talk.
to make it brief, though. The line is long.
Oh, yeah, sorry, I didn't leave much time.
But that's fine. Go ahead.
I'm just going to do this so I don't have to like crane my neck. Excellent talk. Super funny and really like just incredible ideas I was not expecting. Embrace death?
Right, do you want to ask about embrace death?
Of course.
Right, okay, so embrace death is, I'm going to go all the way back, is this mantra that I've been using in another project called the Taddy Web, which I gave a talk about a few weeks ago. Go look on toadpond.com and look for Death of the Taddy Web. But it really takes on board robust first principles. And robust first computing is when you really lean into the non-deterministic execution of code, right? Where we expect code executions to fail, right? So it's like, you can say, yeah, embrace death of code, embrace failure of code. I think one way of coding is to try to avoid mistakes. Another way of coding is to try to embrace mistakes and just be ready for them. So that's embrace death. It's not as dark as it sounds.
Very cool, thank you.
So I wanted to ask, because what you are describing seems really to me like some semiosis, which is the process of transferring meaning of the thing we are talking about. That is pretty prevalent in like human studies or like social studies.
Mm-hmm.
Is it something that you consider? Like we already have some framework of describing a meaning. I think this one is nice as well, but have you considered them together sometime?
Yes, and there's more, you should read the essay, there's a bit more on that. I think one of the things that I think is important is this is just yet another lens for looking at things, right? It's not made to replace anything. I think it's been interesting to see what kind of contexts this can be helpful or actually not helpful. But I think, so I don't want to take up too much time, but yes, I think it's not supposed to be the one true way of seeing things. It's just, hey, here's another way. If the others don't work, you've got another one to try now. Yeah.
Hi, this was a really interesting talk. I was wondering, like, when I think of code, I think of it as a tool, and so like it's in service of some sort of like engineering goal, like there's a goal.
Yeah.
So I'm wondering if this lens produces like an ethical obligation to engineer language to fit some sort of goal.
Right.
Like, I guess I'm thinking if you've heard of like conceptual engineering in philosophy.
I
like
have
that
not.
Okay.
I'm so pleased you mentioned this. I'd love to learn more about that. Yeah, but that's really interesting, saying like code is a tool, and I think that's how I think about like communication. You know, like when I communicate, it's one of the many tools I have to, I guess, like interact with the world, right? But I'm afraid I don't know anything else than that. But I'd love to speak afterwards.
Okay,
that sounds really cool. Yeah.
So I think this is kind of echoing from some of the previous questions, and I'd love to just talk to you more after. This gives me ideas for kind of a few papers, because there's things in here that feel like echoes of like kind of like Foucauldian perspectives on discourse, maybe like some Hegelian perspectives on contradiction. And I guess my question is like, if you go back to like some of these big philosophers who talk about, you know, discourse and language and all of these things, are there particular ones that you're most interested in bringing this work into conversation with in the future? Or is it just kind of like sky's the limit, you know, go where the night takes us sort of situation, embrace the death of it all?
Right. Great question. The sky's the limit.
Perfect.
So one thing I would say, boom, step by step, right? It's this little like mantra and slogan where I think we're trying to figure out what this is bottom up. It's not that we have like a top-down perspective with certain goals. I think this is part of I guess this robust first style of meaning building, right? Is to like build up our primitives, and one of them is natural code. Yeah.
Right. Thank you.
Thank you.
Loved your talk, by the way.
Thank you.
So I just started reading on the plane on the way down here. Irving Goffman's book, The Presentation of Self in Everyday Life.
Right.
Okay. He wrote this in 1959, but it's all about, whenever we communicate, we are performing. There are observers and actors in this, and there's all this stuff that goes on, subtle negotiation about how we communicate.
Right.
And I think that makes APIs much more complicated in real life than in code that is unnatural code. So it would be very interesting if you read that book and thought about it, if there's some other interesting patterns to come up. But anyway, that was just my thought. Yeah.
Thank you. Can you show me that later?
Yeah,
that sounds great. I think one of the reasons, right, this whole idea has been interesting to me is because it's about, a lot of it is about, we can have a look at how we define ourselves, right? Like how we, like you say, like perform in a way, right? And yeah. So yeah, that sounds really interesting. Yeah.
So this is, again, a variation on questions people have asked, but there's lots of literature in psychology from the pre-computer days that has considered how we can understand and systematize and find patterns in our thought processes and in our interactions with each other. But I think part of the thesis, if I understand it, of natural code is that by viewing things from a computational lens, this is generative in a way. It brings us to new insights we might not have had exploring things the same way, but just with the set of concepts that existed like pre-1950. And I suppose API is one of them, but it's still a little bit unclear to me, like, what are kinds of ideas you hope to get through this line of inquiry where it's really like you need this metaphor to, or like this metaphor productively generates those ideas in a way that would be difficult without it?
Right. Really great question. One of the challenges I put to Dave in the essay was, isn't this just a psychology model? And I did a psychology degree, so check out his answer. I would say that one of the big things is it it's more of a blueprint. This kind of model is more of a blueprint for how to implement programmable machines. It's not just trying to observe like how a person is or works. It's about, right, this is how we could implement something. And I could go more into like what that really means. Yeah, I should probably end there.
Okay, thanks.
Maybe some last comment. For, quite some time now, I've been wondering, coming from a Smalltalk background, what makes a good Smalltalk programmer, what makes a bad Smalltalk programmer, how to teach these practices quickly. Also coming about exploratory programming, what does it mean? How do you think about your problems? And when I saw this, jump to social coding and how to, better interact on a social level, it reminds me of teaching, and then maybe there's a way back to program these other machines, like these ones.
Right.
And maybe you have a quick final comment on that. If there's a way back, if you have a better social coding, like this model you showed at the end, is there a way back to this more technical things we're doing right now?
So, I mean, for me, the clearest way back is through this non-determinism, right? Because I think we assume that we assume that things are going to run the way that we expect all of the time, and partly because we can't always rely on that in the real world when we're trying to make things for the real world. And so far, I think that we should make things for the real world, so we should be interested. But sometimes we just make mistakes, and then we code things in a way where we should expect some mistakes, and so we should embrace the non-determinism of that. And I think there are some huge blind spots. There are some huge blind spots in computer science because of this sort of addiction to determinism. And the thing I presented last year, the reason it worked was because it was fully non-deterministic, and so it hadn't been done before. So I think there's lots of low-hanging fruit for non-deterministic computation. So I'd say that.
Thanks again for the talk. This brings us to the coffee break. So be back in 30 minutes, I say.
Okay, good afternoon, everyone. Welcome to another Onward session. My name is Stephen Kell from King's College London. I'm your chair for this session. We have 3 talks, 2 of which are paper talks, 1 of which is an essay talk. And our first talk is from Mark Maron from the University of Kentucky, who will be talking to us about a programming language for data and configuration. Is that right?
You got it.
Okay, take it away, Mark.
All right. So I'm very excited to come talk about this. I loved the keynote this morning. It's set up beautifully for this because we're going to talk about a programming language for data configuration. I was going to put and APIs on there too, but it was getting a little lengthy, so we'll stick with that. So, you know, is data a boring problem, right? Like, I mean, programming languages are about application logic and all this cool stuff, and data, well, I mean, it just like, you know, kind of sits there, right? And how many problems can data really cause? It's simple, right? Application logic is where all these crazy things happen. And, you know, don't we have a bunch of standard representations? We got JSON, YAML, XML, right? That's, you know, put the data in there, everything's great. Well, not quite. I want to tell you how exciting data is, right? It's the heart of a company, right? The most valuable asset in many companies is the data they have and their ability to extract value from it. And oftentimes, you know, it's sensitive or critical to our everyday lives, and we're getting increasing pressure from regulatory and other bodies, you know, putting constraints on how this data is used, spread, tracked, and everything, right? You can imagine stuff like customer and sales leads, critical. Like, I'm a CRM company. That's my moneymaker, is these leads. Obviously, medical history. I'm very sensitive about how my medical data is stored, moved around, who has access to it, right? And I'm going to, just a little cliche, but we're literally in the information technology sector. It's in our name. Companies need to know what they have, where it is, and how it's used. This is a fundamental problem. So now that I got you excited about that, let me point out a few practical impacts of data errors. So in 2020, Citibank got fined around $400 million for poor data quality practices and denying people some loans based on corrupt and incomplete data. And they were put under a consent decree that they needed to fix this post-haste. Well, 2024, this summer, the Office of the Comptroller of Currency also assessed another $75 million penalty for not making enough progress to address these problems, specifically, you know, the impact of data quality concerns on regulatory reporting. So big money in data, right? I'll also point out another $150 million fine against Twitter for taking phone numbers that people gave for 2-factor authentication to do advertising. Now, not only is this a big monetary fine, but you have a big impact on, you know, brand quality and customer retention. People get really annoyed about these kinds of things, right? And, you know, it's kind of funny, probably everybody's seen this a bunch, but it happened just a month ago. Okay, 8.5 million computers put in a boot loop, grounding a bunch of flights, disrupting the NHS, and a bunch of other stuff for a couple of days. Now, there were many things that went wrong, but what was one of the culprits? It was a custom data format with a custom parser forgetting to do a little data validation and taking 21 fields and cramming them into an object allocated with 20 slots, right? And bad things happen when you stick that extra field on the end, right? So, big practical impact. And, you know, you say, well, okay, maybe, you know, maybe they were using the wrong thing. Maybe we should use X, then. But they already do, right? A lot of existing formats, they're imprecise or incomplete. A fun problem for everybody. Take a 64-bit int and put it in JSON. It's a fun encoding problem. You know, schema programming still map to a language representation, and you still have to do a lot of parsing. And if you're doing stuff, some people use Java, some people use C, and you're putting everything in XML, everybody still needs to parse that XML and put it in their own internal representation. And if you have teams that are producing a lot of data and want to collaborate, this one's using JSON, this one's using XML, you don't care about how the data is represented. You care about it as a logical entity. And you know, a big one that really is a surprising addition is a lot of domain requirements aren't just structural. You have these logical and expression requirements as well. Sometimes field A is null, implies field B has some particular expression, it has to be positive or something else. So it's not just I need to define the structure of the data, but I need to define a lot of logical relations on the components of the data to ensure validity as well. Now, I'm going to say these problems are solvable. And the great thing is, we already have the tools to solve many of these problems. Type systems are designed to describe logical compositional structures of data. They allow composition, inheritance, building structures up of subcomponents. We have error detection. The great thing is now you can do versioning, right? You don't need to know was it version 1 of the data, version 2 of the data, version 3 of the data. We already have that, wrapped up in package management and all this great stuff. So it really comes down to how do we apply a lot of good techniques we have from building a type system for PL to building a type system for a data model, data language. And there are a couple of interesting subtleties here. So one thing is, we don't want to pick up the nuances of one particular programming language. We don't want this to be a data model for C++, or we don't want this to be a data model for JSON. So it should be polyglot. Like if I'm building a system that talks Java, JavaScript, and Haskell, they should all be able to talk in the same data format. We need an expression language for validation. It's kind of an interesting little bit to tie into this type system. And it's a funny thing. For all I'll complain about JSON, like in its many quirks. It has an amazing success story of making it easy to author literal data and use this for configuration, test cases, just using curl to test a REST service, human readable, it's great. So we'd like to build on this and have a very uniform encoding that doesn't have all those quirks, but gives us this nice, easy, malleable, interactive way to work with data and systems. So how do we go about doing this? Let's walk through an example. I'm not going to go into the nitty-gritty, but I just want to give you the flavor of some of this. So I went to the National Weather Service, and they have a cool RESTful API where you can send it a location, and it will send you back a forecast for your current location. And I've simplified this. I mean, there's a lot more there, but it has like a low temperature, a high temperature, a field called wind speed, a forecast percent. And you might look at this and say, well, this is the National Weather Service, so everything is going to be in US units. So it looks like a very cold day, but you might have not noticed that, well, hey, actually it has an extra field called units, which may or may not be present. And in this case, it says it's SI, so it's actually going to be a very hot day. So, if you're just using this swagger style of let me give you some example records with some sample fields and you can kind of intuit what they are, it's very easy to shoot yourself in the foot and have some bad experiences. So let's convert this from just this random record and examples. Let's actually make this a type. Oh, sorry, let me show you one other funny thing just to give you the real flavor here. National Weather Service has also started rolling out an open API spec, which is a very popular way to specify RESTful services today. And I just took a page, it's a little bit, it's 6,000 lines of code with lots of stuff where it has some description and some other stuff and all this good thing. But I want to point out a couple fun little bits. So first off is it has a thing called end time, which is given as a type of a string, but its format is a date time. So rather than actually having a date time as a logical thing you can parse, it says give you a string and now you're responsible for parsing the date and the time correctly. It's an ISO format, but good luck getting that right. So all this adventure, everything turns into a string on the web. Another funny one, okay, it's got a name, which is a string. Oh, but it says this value isn't present sometimes. So it's not really a string, it's like a string or null or an option string, but you wouldn't know that unless you read the comment. The other thing is, here's an example of what this string could be. Tuesday night. Okay, so is this like, could this really be any string, right? Could this be is this like some Tuesday, day of the week followed by day-night string? Like, who knows? You just, you kind of guess. Maybe you curl a bunch for a little while until you feel lucky and you're gonna make up your mind on what it is. But no, we want a much more concrete, analyzable, grounded thing. So here's our definition of this forecast in our Bosky data description language. And now let me be really upfront. This has kind of been a project that I've been working on with some great folks in the fintech sector and at Microsoft, and we've been swapping ideas around. So there's a couple cool projects with a lot of the same flavor. But this is the particular one that we took as kind of the greenfield North Star. We're going to go and we're going to take the idea as far as we can without necessarily a lot of practical concerns. So as you can see, it looks just like a class definition, right? And we can do inheritance for composition. We have enums, we have numbers, we actually have real floats and real ints and all this good stuff. And then we can declare an API as a special type of function that's going to get exposed as an endpoint. So this already improves on it a lot. Now we have a concrete thing with fixed semantics and we can reason about it. But we can start doing a little bit better, right? An easy table stakes one is to allow type alias declarations. So this is like a new type. So we can say, hey, temp range isn't just an int, it's a Fahrenheit, and we're actually going to put that in there, and then you won't get your Celsius and your Fahrenheit confused just as type structures. This is great. But we can start being more fun. Like, we care about data validation and data quality. So maybe I have forecast percent. It's currently declared as a float, right? I could new type that as a percentage. But I'd also like to be able to new type it and then enforce some constraints on it so that it should always be greater than or equal to 0, always less than 100. And we want that to be checked automatically when you're parsing these, importing these, everything. So you don't have to worry about, bugs in your parser and validation logic, which are one of the top issues that pop up in web services, kind of unsurprisingly. But let's keep going a little bit more. So we also had these weird sort of structural strings. Like, there was some semantic information crammed in a string just because it was the same thing everybody talked, but it really had semantic structure. So we want to allow people to express this semantic structure in a precise way. So you can say, here's a const regular expression that is showers, thunderstorms, snow, or fog, easy. And then you can declare, I want forecast detail to be a string of some other regular expression, which can actually compose these const regular expressions in. So you have a nice composable way to describe, if you have a string, is it truly an unstructured string? Is it a semi-structured string? What's that structure? That structure is reusable and composable across the way. And this turns out to be incredibly, incredibly useful. And I think there's a very interesting opportunity to do a lot more with structured data and string languages to solve more problems than you can do with just regular expressions. Like I said, a big win we have is being able to do logical validation. So of course we can put in some simple preconditions like, okay, don't pass me the empty string for the city name. It should at least contain a couple characters. But you might also have other interesting stuff, like if I get a forecast, the low temp should be less than the high temp, right? And the wind speed min should be less than the wind speed max. And of course, since we're good programmers, we don't want to just put these on an API. We should put these in the typed as validation invariant so that they're enforced everywhere, and it's very easy and obvious that these are checked and are always correct. So then I said we want to have a literal representation. So this is kind of a nice way. We want to make it really easy to author and read these values. JSON is very nice. A couple pain points it has is it doesn't have a good representation for all types. A lot of stuff gets crammed into strings. And there's all sorts of tagging issues. Some people will use tags on the object. Some people will use envelopes. And there's always conflicts in the way it's done. So if we just clean some of this up, we have a really nice way to say, hey, I want to write a forecast value by hand. And we can do it with explicit tagging on the left there. Gives this nice way to say, here's a forecast between 33 and 52. The ints are explicitly tagged as Fahrenheit. So you can read this and understand it pretty quickly without any additional information from the type system. If you have a big document, having to explicitly annotate everything is a bit of a pain. So it's nice to be able to elide this in cases where you know what the type is. So you could just drop the explicit temp range or Fahrenheit parts on these values. So this makes it really easy to author configurations, to use this as a fairly efficient but still human readable data transport format. And its convenient thing is it's still very efficiently parsable. Okay, so hopefully you're like, hey, this is cool. This solves our immediate problem that we have in this data API spec space. We can describe what data a program takes in very efficiently. We don't have to worry about parsing and validation bugs. We have a great literal format we can build to communicate across polyglot services. I think that's super exciting, and a great way to show the value of programming languages in practical problems. But we'd really like to build on this to address other challenges, right? So when I'm setting up a service, I got to deal with testing, I got to deal with mocking, I got to deal with versioning. I'd really like to make it AI accessible, right? So how do we build on this, bringing PL concepts to data to enable some of these scenarios? So I don't have time to dive into all of them, but I'm going to hit 3 that we've sort of done some prototype work on just to give a bit of flavor of this. So let's talk about mocking. So unit testing code that just adds 2 numbers is pretty easy. Unit testing code that does some like, compiler transforms, is harder because you got to do a lot of data setup, but not too bad. What really gets you is I'm now going to do unit testing on my microservice that depends on other services. So let's say I'm going to create a sailboat rental application, and I'm going to check the weather forecast and decide if it's too stormy to rent you a sailboat today. So what do? Well, I either call the National Weather Service as part of my unit test, and now I have a flaky test. I decide to create my own copy of the National Weather Service and put it in some sort of weird sandbox and run it directly. Or I go and I manually write a bunch of mock data, which nobody ever does because it's a huge amount of work and it's always out of date, and then you only test the happy path, right? So this is super unpopular. So instead of doing this, let's use the fact that we have a great structural description of our data as a type. And in this logical language that we have for putting constraints on it, we've conveniently constructed it to be very deterministic and easily encodable to SMT semantics. So now we can ask a solver like Z3, hey, when I'm running my unit test, if I have a value, go and just take that service and generate me a valid response, right? We can tune it for natural values, random values, whatever, but we don't even need an implementation of that service. So here's a quick example. We have that forecast going there, and I'm going to go, I have no implementation. I'm just going to evaluate it with certain inputs. So I'm going to say, hey, I'm going to give you a city name, Albuquerque, and you generate me a forecast that is the right structure, the right types, and all of the constraints are satisfied. I'll give you another one, Phoenix, right? And it'll generate a forecast that has all those constraints satisfied. Now, I'm just solving for a possible solution. So you'll see it's predicting snow in Phoenix, right? Which might not be the most natural solution there, but you could ask an LLM to fill in some of these values and then validate with the solver as well. But this way, I don't actually need a service. I can just execute a service from its spec, plain and simple, right? So this is super cool. Another fun one is AI programming, right? So suppose I have a simple, really simple service, or I'm going to just use a function in this example, that's going to find some pair, and it has a signature, and it has some constraints on it. And really, LLM agents, they don't always get things right the first time. So it's nice to give them a couple test cases, right? And then you kind of winnow out wrong solutions. So you ask the programmer, all right, we got this great literal syntax. Go ahead and write your input-output pair in the examples there, and we'll go and synthesize this body for you. Now, nobody likes writing a bunch of input-output pairs and trying to, kind of scratch their head and think what values are interesting. So let's come up with a different approach. Let's go and actually take this, put in a keyword defer, and we're going to allow you to execute the program. So we'll put a bunch of calls to find max pair in there. You're just going to run the program. There's no implementation. That's cool. We'll just run for a while, and if we hit one of those, we'll pop it up, and we'll say, here was the input. Can you write the correct output for that particular function? So, okay, we do that. We'll run it again. It's actually got one duplicate input, so it can use a memo table. It keeps going there. Finds a new input. We give it the answer there. And there you go. Now we've got our set of examples all built up, ready for the AI agent to synthesize that. And even the better part was I could start writing my code. I could start testing my code. I didn't need to implement anything. And now my AI agent can do all that work for me. Building on that, very fun thing is, suppose I'm now using an AI agent to do some work for me, right? And how is it going to do some work for me? I'm going to expose some APIs that it's going to be able to call. So here's one that's useful, especially if I'm in fintech, I'm doing trades and I need to pay somebody. So I'm going to take some amount of money from in US dollars, and I'm going to send it from an account to an account. Now, would you trust ChatGPT with access to your bank account with this API, right? I mean, it's probably usually statistically going to not wire $10 million to, some strange country where I'll never get it back from, right? But you never know, right? It's a statistical agent. Well, I'd really like to provide some sound guardrails. So the great part is we have this ability to put requires and constraints on what an API does. So we can say, hey, I am going to demand that under no circumstances will the amount ever be larger than payment limit. So I will put a hard guarantee on how much this agent could ever transfer. I could also add other things like I must have maybe a valid bill in order the to account must appear in a valid invoice in order to make a payment. I can put other things, but I can put a concrete semantic guarantee that this agent will never violate this property, right? It's not just a statistical guarantee, it's a well-founded guarantee. Interestingly enough, there are other things you can do. So I might want to allow an AI agent to schedule meetings, right? So I say, hey, you can schedule a meeting on my calendar, you give me a time, you give me a list of attendees, it's all great. Now, in theory, you know, maybe scheduling a meeting at 4 a.m. on Saturday is cool. Maybe that's the right thing for it to do. But in practice, I probably don't want that, right? So what I'd really like to do is be able to put a soft check on that API and say, like, look, you know, you can schedule a meeting at 4 a.m. or outside my working hours if you want. But if you do, I want at least to be able to verify that that may or may not happen. If it does, I may want to take some action like reconfirm with the user, do you really want me to schedule this meeting at 4 a.m. or re-rank possible solutions for one that, you know, doesn't pick such an odd time. So what's the conclusion here? Well, hopefully I showed you some exciting stuff, but, you know, I think data configuration, API specification are actually really critical issues in software systems. And they often get overlooked in, you know, the programming language community because they're not that core logic, but we have a ton of tools that apply really well to them, right? Data is the foundation of computation, and parsing and validating is surprisingly hard and buggy, real common source of errors. So, and I think, you know, in the second half, hopefully I showed you that improving and, you know, semantically grounding some of these things actually opens some amazing opportunities and advances in other areas, right? Testing, traditional software engineering, but also allows us to have a real voice in this sort of exciting space of how LLM agents are growing and being put together. And in particular, this notion of verifiably trustworthy agents, not just statistically trustworthy agents. So I'll close out, just got a couple links here. We got some projects up there. You know, an interesting paper we did with some folks on, you know, programming and these data issues in the fintech area. And I also want to thank some of my key collaborators, Brian, Stephen, and Richard, right? It was great to get their input on this, and they really had a big impact. So I think that's it for me, and I hopefully have a couple minutes for questions.
Thank you, Mark. If anyone has a question, please step up to the microphone. And if you could give it a quick tap to check that it's on, I would be very glad. Perfect.
Hi, thank you. That was really, this looks great. So I often get very frustrated because I have I'm writing types and I'm writing validators separately, right?
Yes.
Within web development, usually like with Zod or something.
Oh, okay, yeah, yeah.
Right?
Yeah.
And, but sometimes that feels annoying, but sometimes that feels kind of right to me, you know, to sort of have this like separation. Like, can you, I was wondering if you could talk more about like what your view is on that. Like, do you really want them all together all the time, or yeah, how do you see this?
Well, I think this is the interesting, this polyglot world, right? You really want to have a central point of truth about what a user is or what an account is. And then from that, you want to be able to generate the appropriate types in the languages that your system consumes, right? Like, you'll want to be able to generate those representations for SQL database. You want to be able to generate those representations for, you know, a RESTful API. You want to be able to generate Java types from them. So I think that's really this separation of what is our logical model of data, and then what's the physical version everybody consumes. So I think that's kind of the way I view that splitting, right? If that makes sense.
Yeah, so it's like something like higher up, perhaps. Like
yes, and let me focus. So yeah. Brian Turleson is working at the Azure service where they have this problem where they're building SDK. You know, they have one service, and they're building SDKs for it in a bunch of languages, and they have a bunch of versions in each of these. And it's like, we do not want to try and keep all of these and maintain. We need a central point where it says, this is what the service does. Everything else flows from that, and we have guarantees that they're all consistent, right? Nobody likes making a call in Java and the same call in JavaScript, and they don't work, right? Because of some parsing difference or bug.
Thank you.
Thank you for taking on this problem. This is something I've fretted about for a long time. We have long had the situation that the programming language algorithms strain of programming and software engineering has shouted out the data representation portions. And this this came fresh to my mind a few months ago when the CrowdStrike outage happened, that it was so much related to data, and the company was in fact in their initial report saying, but it was only data. So previously I had a run at this and didn't make any progress and gave up and went away. But a long time ago, when I thought about having a run at it, I looked at the specs for the standards for electronic data interchange. And one of the reasons that I shied away from it is because they were so complex. There were layers and layers of complexity. There were whole fields that were dependent on the values of other fields. So my question is, how far into the complexities of serious EDI do you go? Are there things about EDI that cannot be described in regular grammars? Is it just a matter that it's complicated, or is there some deeper semantic complexity?
So I think in this one, the goal here is to create, it's just like a programming language type system. The goal is to make it easy for separate teams to develop logical models for their data and then exchange, compose, and version these effectively. Now, one of the issues is you won't be able to generate from these physical models for encoding this data. I'll swap you out. Now, one of the things is you're not going to be able to generate as efficient an encoding as, let's say, if we were doing this from gRPC, right, where your definition is closely intertwined with the physical encoding. It's just like working with Java versus C. Well, I can squeeze out more performance in C because I can twiddle individual bits. In 99% of cases, it doesn't matter. For these RESTful services, they're much more concerned with correctness than getting that last 1% of performance. So I think this is a place where we trade off some of the complexity for general simplicity and reliability and usability.
So you're saying that the real issues that arise out of commercial grade EDI are issues of efficiency rather than efficiency of the ability to represent?
Yeah, that's how I'd frame it. Yes.
Thank you.
Yeah.
Thank you. I have to be a really brutal session chair and cut the questions here, but I'm sure we can take them offline.
Okay.
Let's thank Mark once again. Our next speakers are Jonathan and Joao. I've forgotten what order you're going in, but they're talking to us about something very intriguing called the Meerkat vision.
Thank you. So we're going to talk about Meerkat, which is a vision for a future in which we can build reactive web applications and have first-class language support that provides live updates and scales to the kinds of apps we build today. And this is a collaboration between Joao and myself. So my personal motivation for this was building an app called Noteful. Noteful is a free app that teaches music notation and theory. You can check it out on the app stores or noteful.net. But what I learned as part of building this app is how do we build apps these days, right? And a big part of it is something that originated as functional reactive programming, right? In fact, Noteful is a packaged up web app. You can run on your phone. It uses the Angular reactive programming framework. And the benefit of reactive programming is essentially declarative UI programming. You describe in a declarative way how pages in your UI are constructed given the data in your system. And when the app data changes, the framework detects this and the pages are automatically updated. So it's super cool. It gets rid of a lot of the kind of hand munging updates from the UI to get to the UI from your data. But all is not right in paradise. Okay, so in industrial reactive programming, you can connect data on the client with the UI. But in fact, in most modern web apps and mobile apps, data is actually on the server, right? And access to the server is not usually by a reactive query. It's by an old-fashioned, non-reactive query to the server of the database, like pulling new data. And so this creates an impedance mismatch, and the programmer is forced to solve it. right? The programmer must keep client-side and server-side state consistent, which is a source of lots of complexity and lots of bugs, and I've experienced these myself. So, furthermore, reactive programming frameworks really give you this update of data automatically, but code updates are still hard, right? And in fact, they're highly error-prone. You have to do this dance where you update the database schema, and then you update the data in the database to match the new schema, and then you update the server, and finally you can update the client. But by the way, if you get any of this order wrong, or you're not backwards compatible, because the clients aren't going to be updated immediately, this goes wrong, right? And your users see the pain. So there was this awesome work from actually 9 years ago by João Costa Seco and his student for a way to do this much better, a live reactive programming model. And João will give a demo of what they've been working on.
So let me show you what we had 9 years ago. And so we had 3 simple constructions to define a web application. So we could define a variable. That is the symbol here for a database table, something on a server. Okay, let me change to my IDE, so quite simple. And so if we paste here the command, and here every time, this is a live demo, so it needs to take a while, right? Oh, wait. What happened? Shall we switch to the backup?
We just tested this. We can switch to the backup if...
So...
Yeah, try it one more time.
No, it doesn't. It lost the connection. Okay. That's not good. Yes,
there you go. You see the issues.
Plenty of issues. Okay, maybe we can switch to the backup. And the backup are some slides that we have stored at the end of the presentation. Here, right? So the idea is to have, well, now I need a pointer. The idea is to have some language to define the state of the application. Okay, so we just say var minutes equals 0, and then something to define the logic of the application. And you can say, okay, now I define a name called seconds, and it's minutes times 60. Okay, and the third ingredient is, okay, we have state, we have logic, how do we change the state? And we define simply a data type, which is actions, and actions contain assignments. Okay, in this case, increments minutes. Of course, we can define a few more names, and using an HTML-ish part of the language, we can define a user interface. And what you get is here, what you would get if the thing worked. Okay, so what happens is that if you immediately use the button, you get 60 seconds. Okay, you can keep on using it. Behind the scenes, what happens is that you have state, and then you have 2 definitions depending on that state, and that reactively update whenever the state is updated. And then, of course, you have UI over there, which is just another value of the language. Okay, so whenever you tick, then the state is updated and everything is propagated immediately. Okay, we can then keep on going and defining new functionality by having a new definition. So now we want to reset the minutes, but we want to add that to the UI. So by redefining the definition called buttons over there, by redefining the whole definition, immediately all the clients that were using this definition are updated not only with data, but also with code. So a button appears in everybody's user interface because it's been updated in the code base. So of course, what happened now is that we redefined the buttons, and all the pages are updated. The third step that we want to do is, okay, it's a bit dumb to be counting minutes, right? What we want to count is seconds, and then show minutes. So we can now redefine seconds from being a definition based on minutes and say, okay, no, seconds should be a variable, so the state should be storing seconds, and the current value is minutes times 60. Okay, then we probably should redefine the increment action and the reset action to, instead of changing minutes, to be changing seconds now. And not to lose any of the definitions before, we change the minutes, which were the state, to a view of the seconds. Okay? And then there's a detail here, is that we want to do this in one go. Because this system lets you update code and data concurrently. So, well, it sequentializes everything so that everything goes well. But if you do these 4 things in a row, you may lose data because someone may increment the minutes variable that was no longer in use in between these instructions here. Okay? So your interface looks the same, the behavior is the same, but the state beneath is different, completely different. So, and we do this in an atomic block. So yeah, you are still counting minutes, but underneath you're counting seconds. Okay? So, and this is, so we switched from minutes being the state for seconds to being the state. But yeah, we need to count seconds. So to count seconds, well, we define a new function, a new definition that increments the seconds, and we add that, not to lose the tick button that counts minutes. Now we have a small tick. And what happens now is that whenever you call small tick, you count seconds and not minutes. And that's, well, the same dependency graph is used in order to propagate the data changes from the increment seconds over here, and then change seconds. It also changes minutes, not used anymore, but then propagates to your user interface, the proper changes. Okay, and that was the demo that I wanted to do live. Didn't work, sorry. But so let's go back to this. Get back to Jonathan.
All right, so this is a super cool programming model from my point of view. It provides some fundamental constructs for building reactive multi-tier systems, such as the state variables that you saw. We also have tables, pure computation that computes interfaces from those, and of course, any state changes are propagated along the dependency graph to the UI. Furthermore, it's reconfiguration of state and code, and it's all type checked, so you know that your live reconfigurations won't break anything, at least as far as the type system of the programming language. There's more features like making sure there's no cycles in dependency graphs, so that propagation stays finite, and we have glitch freedom, which makes sure that you don't see kind of artifacts from variables being updated in the wrong order. However, there are also some limitations, right? At this point, it's a programming model, one that sometimes doesn't work, right? It's not an industrial scale framework. But a bigger issue is that the semantics are really for one centralized system. Because there's only one server, it's not scalable to large amounts of data, large numbers of clients. It's not scalable to large organizations where you might really care about modularity of implementing different services. And there's a sequential queue of execute and update operations, which actually gives us some very nice properties, but also limits scalability because we can't do anything concurrently. So fixing this requires some programming language ideas, right? Modularity, some distributed system ideas, availability and consistency, ways of synchronizing truly distributed updates, as well as extensions to things like the data model, providing the ability for disconnected operation in case the Wi-Fi comes down, right? Maybe the demo can still work. And software lifecycle, we'd like to provide more software lifecycle support and interoperation from a software engineering point of view. So we've expanded this initial prototype into a vision for a future that we call Meerkat, after the colony of little animals that work together to do great things. And our goals here are to support linguistic reactive programming, right? Where you have this nice model of computing interface from data and updating the interface when the data changes. But we want to make the reactivity go across the whole stack, where the stack can be, not just one server machine, but a whole network in the cloud and on your local device. And so we have this notion of services, which are, can be in the cloud or on your local device. They can be replicated. They can be sharded for scalability. They can be on your local device so that we can support disconnected operation and local first software. Maybe these, you need to customize the kinds of semantics these services provide in terms of consistency guarantees, for example, or provide more interesting kinds of data models than what we support right now. And of course, we'd like to make these live code updates distributed and provide some DevOps support of the kind that you see in software engineering research, but with some nicer semantics because we control the programming language. So let's talk a little bit about what these mean. Linguistic reactivity. We want a bird's eye declarative view of the system architecture for programmers. This really enables a lot of later goals. The ability to control custom semantics from one place, the ability to do synchronized and type-checked live updates, to provide more DevOps insight than you can in a system with a lot of layers and frameworks. Across the software stack, we want the UI to react to server data store updates without requiring the programmer to write any glue code, right? In Joao's demo, the UI definitions just reference the data, right, on the server. We also think it's useful to really have a data store that's conceptually imperative actually be imperative, right? I love the model of Elm for programmers, but I don't necessarily love the fact that the data model is a stream of functional values, right? It actually makes expressing things more complicated in my opinion. There's some examples in the paper that go into that. But we want type checking, right? We want to assure consistency across clients and servers, things like data formats and operation signatures. We want termination checks, as mentioned already, in the live updates. There are some reactive frameworks that kind of move in this direction, like Meteor and Rescala, but we believe there's really value in having a language here, right? A framework can't give you as close a match to the user's conceptual model as a language can. Some boilerplate still is necessary to connect the client to the server. See the paper for details. And of course, in a framework solution, we lose some of these benefits of type checking and certainly safe live updates. So what's the key to making this attractive model really scale? So we believe the key idea is that of a service. In our model, a service is a modular unit of development, of composition, of deployment, and of updates. It's analogous to microservices in modern distributed system architectures. So we want to define services using the kinds of constructs Joao demoed. We want to have signatures that can export definitions and actions, but perhaps hide internal state like variables and tables at your option. We want services to compose, just like one microservice can use another. Imports can be specified by signatures and URLs, or you can make them dynamic using a kind of functor-like construct that allows dynamic binding between these things. We wanted to provide the ability for these services to be developed and deployed independently, either by different organizations within a company, or maybe even different organizations working together as peers. Live updates, now they can be scoped to a service and not affect the outside world, or they can go across services and allow several services to be coordinated and updated together. Location is important, right, in distributed systems. And there's a new paradigm called local first software that really emphasizes users' choice and how their private data is managed. And to support this, we want Meerkat services and data to be locatable, right? So you can put things on the user's device to support disconnected operation or privacy. You can replicate it to make access anywhere. It's what you want. In the longer term, we'd like to explore ideas like inferring data and code location kind of within this system, because again, we control the distribution, so we can use confidentiality specifications, size of data, device capability, sharing between users as a way of directing this. we'd like to, we know that one size does not fit all for distributed systems. So with Meerkat, we're looking at providing a default level of causal consistency. We're choosing causal because it's basically the greatest consistency you can have that's available to sub-partitions and has fairly good scalability characteristics. There's no global coordination necessary. But we also want to provide an option and support, explicit support in the language for eventual consistency, for greater scalability for those who need it. And of course, standard ideas like replication for reliability or sharding for other dimensions of scalability in data. So we want to provide some great defaults that we think a lot of people will use. And I think it's a story of programming languages that if you provide a few really good things, people can use the tool effectively. But again, two sizes also don't fit all, right? So we'd also like the ability for people to plug in their own database, maybe a commercial database that's reactive, and definitions become select queries, actions become insert updates. And then looking at more interesting data models that we don't support right now, like referential integrity, for example. Just to give you a little bit of technical material on how we're thinking about some of these issues, I wanted to give a little advertisement for Historiographer. This is by Julia Freeman and Timothy Zhao, who actually presented a poster in the student research competition last year and won. So Historiographer gives you causal consistency and glitch freedom. To give you a little bit of an idea of what this is, consider this example. We got 3 variables, 2 definitions that depend on them, and 3 different actions. What the actions are going to do is, to make sure there's no interference, they'll acquire read and write locks on the variables that they affect, right? And so actions 1 and 2, they both access variable y, and so they'll be mutually exclusive. They cannot interfere. So for causal consistency, we want to track and honor the history of updates. And so if action 1 locks this variable y first, then before action 2, for example, then this definition S here, right, will see the update from action 1 before it sees the update from action 2. So that's causal consistency. Furthermore, action 1 is going to update both x and y, and those are both going to affect definition S. But we want those updates to arrive together, right? Because otherwise you're going to see values of the definition S that don't correspond to any possible x and y, right? And so that's what's called glitch freedom in the literature on reactive systems. But just to give you one more example, action 3 here touches some different variable z, right? And that's okay. Action 3 can run completely independently of action 1 and 2. But because we have causal consistency and not serializability, these definitions might see the updates from action 2 and action 3 in different orders. And that's the price we pay for not having global synchronization, right? If you want global synchronization, use our plugin, add a database. So the final thing we want to look at is distributed live updates and developer operations. So we want to extend Historiographer, which the initial prototype was just about data. We want to support the code updates, including non-monotonic code updates that can break existing code. This gives us maximum flexibility, but it will require some locking and delays. Of course, if some devices are disconnected, they can't be updated, right? And so we're going to have mechanisms for handling exceptions that might be related to asynchronous code updates. We also want to look at staying completely monotonic. This is a pretty common strategy used today, but we can provide some key new advantages. So when you deploy a new service, we can check that it doesn't break anything in existing services. I think the tierless view, the type checking, the atomic deployments make everything easier compared to today's infrastructure where these operations are typically pretty challenging and sometimes slow. And then we want to provide DevOps support to give developers a great experience, right? Imagine preparing an update because these are declarative and updates in code, we can replay them sequentially in deployment, test, and production in exactly the same way. And it's all type checked and safe. Furthermore, I think having control of the distributed system gives us the ability to do visualization and debugging that can give people a lot of help in addressing issues with the programs that they write. So we are working on building this right now. Our first goal is to take the prototype that you saw and make everything distributed, right? So we have distributed modular services with safe live updates and causal consistency. And we want to make it fast. We know people care about performance. So we'd like, since we're going for causal consistency, we'd like to demonstrate scalability beyond what you can get in a sequentially consistent relational database. We're compiling to Rust and HydroFlow, which is a state-of-the-art research infrastructure for distributed systems. We'd like to be competitive with, maybe not exactly as fast as native HydroFlow applications, and then we'll go from there with some of the other vision directions. I want to acknowledge that we're building on a ton of related work, some of which I've already mentioned, others of which is on this slide. There's a lot of cool work in this space, and we just want to bring it together in a framework that will, in a language that will help people write web apps more easily. So that's Meerkat, scalable reactive programming with live updates. Here's a reminder of our vision, and we'd love to have questions, discussion, comments on the ideas.
Very much. We have time for one or two quick questions, but I'm going to ask our next speakers to get set up while that happens.
Hi, Jonathan. Great. I love your vision. I just have a sort of a technical question for you, which is that, in my experience, in general, schema change in a distributed context has to be bidirectional. So when you converted seconds to minutes, there's still code out there that wants to do an increment minutes. And somewhere there's going to have to be something that converts that increment minutes to add 60 to seconds. And I didn't see that in your solution. Have you thought about that? And do you have a solution?
Yeah, that's a great question. So I think the modularity of services and the information hiding of actually giving these interfaces is an attempt to do that. While you can, make you can just put variables out there, which will make your system fragile if you want to. We imagine the best practice, as in object-oriented programming, will be to hide, literal variables and tables behind things that are more abstract, like update actions and definitions. And so then the idea is that you can replace those definitions with ones that work against the new schema in a way that's seamless to clients. And we can check that because it's all type checked.
Okay. Thanks. Great work.
Okay, last call for questions. Otherwise, let's thank Jonathan and Joao again.
Hello, hello.
Okay, our last talk of this session is an ambitious trio presentation, which is very exciting. We have Alan Werfsbrock, Rebecca Werfsbrock, and Jordan Werfsbrock. And I don't know how this is going to work, but it's very exciting already. And they're talking about... Okay, I don't want to rush you.
I don't know what that is doing there.
We have a
She
different paper.
needs to make it full screen.
Okay. So.
Yeah, what the heck is that doing?
What the heck is that there? That's an advertisement for another another thing, but I've lost.
Geez, Alan.
Okay, go away.
So while we're getting set up, it seems a good time to remind you all that tomorrow morning we have a very exciting keynote from none other than Dick Gabriel, who is also sat here in the front. And just like to encourage you all to turn up for that. Obviously, we wouldn't be here without him because he was the founder of Onward. So great to
Sorry.
have the.
That's
That's in
not
the plenary tomorrow,
why
exactly.
Windows disappeared, so. Okay. And this we want to put on the other window, right?
You want to open the presenter view, right?
Yeah, but we can put this over here and get slideshow up there. Yeah, yeah. Okay, and then we want that back on the other screen.
We should have the video off while we're doing the magic here. Okay.
Oh, they all know what goes on behind the scenes.
We're seeing how the sausage is made.
That's right. Okay, now we do this.
And Jordan's sitting there trying not to laugh.
View full screen for that, and then we just need to go over here again, and
full screen.
Is there a menu up there that says full screen?
Got to go over there, full screen.
Oh, hit the green.
Yay.
Yay. Okay.
Okay.
So I think I'm starting out here. I'm Alan. And this is Rebecca. And Jordan's remote. There's Jordan up there. So, this essay is quite personal for the three authors. And so we thought we'd start out by giving you just a bit of background of who we are and where we're coming from here as we talk about this. Rebecca started out as a software engineer doing embedded software. She was one of the pioneers in developing object-oriented software design techniques, and she authored books and courses on the subject. For the last 25 years, she's been a consultant and independent researcher on software modeling, design, architecture, communications, and thinking skills. I'm a systems programmer, and I fundamentally focused on programming languages and their implementation, compilers, virtual machines, garbage collectors, IDEs. I was one of the technical leaders in the effort to commercialize Smalltalk in the 1980s and 1990s, and I was a contributor to the standardization of Smalltalk and JavaScript. Jordan, as an undergrad, thought she was going to be an aerospace engineer, but a passion for writing led her to data journalism, where she grappled with the challenges of communicating data-intensive stories to radio audiences. This led to a PhD in information sciences, and she's now a CS professor, an HCI researcher, and a data sonification expert. And so I guess, like we've covered here, we're all related.
Yeah.
So maybe you've experienced something like this XKCD comic covers. Uh-oh, can't hear you, Jordan. Okay, well, in that case, for this part, Rebecca's going to stand in.
I hate reading your code.
I know.
Looks like the output of a Markov bot that's been fed bus timetables from a city where the buses crash constantly.
Whatever, it runs fine for now.
So does a burning bus.
Okay. So.
No, you're back.
So why do
Go keep on.
Why do programmers so often find themselves in conflict? Well, we've learned our skills in different ways. We were taught different values. We work within technical communities with differing requirements. Maintaining an online transaction processing system running on an IBM mainframe is a bit different from building the front end of a web application. Writing a Linux device driver is different from wrangling a data set to create a visualization. Designing flight control software for a modern airliner is different from scripting a non-player character of a video game.
these scenarios differ in more than the application domains. People working on projects have different programming languages and different tools, and they use different development techniques and have different jargon. If they, they even have different salary scales and career paths. So we call these differences, we say that they have different software development umlautes.
Okay. So one reason we have trouble communicating is that we each have different perceptions about our world. So the concept of Umwelt was first written about by a German zoologist, Jakob von Uexküll, in the early 1900s, and he observed that all living creatures experience life in terms of their unique, species-specific, spatio-temporal, self-in-world subjective reference frames. What does that mean? Okay. Well, if you think about it, a bat perceives a dark night differently than a butterfly or an owl or a human. And the range of different sensory perceptions that animals have is really quite phenomenal. And the hidden worlds of some animals are so exotic and foreign to us that they are almost inconceivable. But just as important, our Umwelts are shaped by our unique experiences. So we come to perceive things by repeatedly being exposed to those things in our environment. If we grew up in a small rural area, as I did, I came to appreciate the gentle sounds of crickets or the chorus of frogs. And then I find them comforting. But a city dweller who comes and visits my house may be unable to sleep at night due to all that raucous noise. So our environments that we shape our Umwelts are unique, and it is only through our repeated experiences that we learn appropriate responses to our perceptions. So here's a pointer. If you are interested in learning more about the amazing ways of perceiving the world that different species have, let alone programmers, we highly recommend this book, An Immense World by Ed Yong. It inspired me to take a closer look at our own Umwelts, and I got my family to do so as well. So one of the things that Ed talks about is that our Umwelt is limited. It just doesn't feel that way. To us, it feels all-encompassing. But they're limited because of our biases. They limit those biases of how we see and perceive, how we hear, what people say. They constrain our actions or what we think of as being appropriate ones to take. So when we come to a new environment, we may not operate very well because our Umwelt hasn't been tuned to these new realities. I can tell you from a small-talk programmer's perspective, going into Java was a big shock. Ideally, when we encounter new stuff over time, we learn about it and unconsciously tune our Umwelt. We then can notice things that we hadn't noticed before, and we learn what's important and how to act. So I've found that most people are not super reflective about how they perceive their world. They aren't even aware of having a unique Umwelt, let alone its history and how it came to be. They simply exist in the moment. So Ed Yong also noted that a moth will never know what a zebrafinch hears in a song, and a zebrafinch will never feel the electric buzz of a black ghost knifefish. But we will never do any of these things either as humans. But we are one species that can try. So while we can't know the Umwelt of other experiences, we can imagine them. But we don't even know our own Umwelts, let alone those of those people that we work with, but we can try. So by examining our personal Umwelts, we believe we can come to appreciate our own behaviors and our preferences and our biases and kind of learn how to work together, perhaps. That's why we decided to explore the concept of a software Umwelt and how it is formed and shaped and tuned over time as a way for us as software developers to understand and navigate the complex and ever-changing environments in which we work.
All right, I want to make sure y'all can hear me.
Yes.
Can I get a thumbs up? Okay, I'm getting a little feedback, but hopefully that'll resolve. So the trouble with umlauts is that it's really hard for us to perceive them. So how do we go about seeing our own eyes or smelling our own noses? If everything we do is filtered through our umlaut, we can never truly step outside of it. So is this task that we set about to do, to sense our own umlaut, a futile exercise? Probably, but we were going to try anyway. So just as pair programming helped us understand our own coding habits and thought processes, we thought that maybe our umlauts might become evident when they bump against those of other software developers. So we, the Worksprocs, banded together to undertake an exercise in social and self-reflection to understand our umlauts. And here we're drawing on self-reflective and first-person methods, which are often used in human-computer interaction and design research. So we set out to write personal stories about our own software umlauts. And here's what our rough process looked like. So first we wrote lengthy narratives on our own. These were roughly 1,500 words or so, using an initial prompt about what formed our software umlaut. And we felt that we each learned a lot about ourselves through writing these narratives. But navel-gazing at our own boring autobiographies was not our goal. We wanted to learn from each other. So next we examined each other's narratives and asked questions like, oh, tell us more. Wow, that's a really weird experience you had. And we left social annotations in each other's documents and responded to those questions. So we had this kind of thread of dialogic back and forth. And from that, we pulled out what seemed to be common threads that occurred in the trajectories of our software development umlauts. And based on those threads, we constructed new prompts to elicit more targeted details. And finally, to add another layer of reflection and synthesis, we each distilled our lengthy umlaut stories into a one-paragraph summary that captured its essence. And now we're going to share these with you. So I'll go first. My software umlaut is tightly coupled with my familiar umlaut, and it's a matter of legacy and identity. It's resulted in pride and curiosity. Writing software requires a type of thinking that we don't often encounter in other dimensions of our lives. We need to empathize with how other people relate to programming. There are many ways to program, and embracing them leads to broader and deeper perspectives and ways of doing things. Software development is a socio-technical system. I'm always looking at systems from the standpoint of trying to figure out what people and tools are required to navigate them. But the real power of software is that we can make things that people use, technologies that change the world. But how do we know that we're making something people want, that they need, that doesn't harm them? To consider these questions, we must always remember to pull back and see the bigger picture.
Software is my creative media, and programming is an intellectual activity that can be done even in the absence of a physical computer. I'm a systems programmer. I value technical diversity, expect ongoing evolutionary change, and relish radical innovations. Lateral thinking is essential for software innovation. I believe that software exists to support humans and human activities. It should be approachable, understandable, consistent, and comfortable to humans that will interact with it. I've come to understand that programming is model building. I can build software models of real and imaginary worlds. They're all the same to a computer. Programming is built from layers of abstractions that are ultimately rooted in the numeric manipulation capabilities of computers.
So the fundamental foundation of my software umvelt is curiosity. It drives me to explore new things, immerse myself in new environments, and I can be uncomfortable and uncertain in my abilities. I am all the time, by the way, while at the same time believing in my ability to successfully navigate new environments. Becoming comfortable with being uncomfortable leads me to find ways to adapt, grow, and stretch my abilities. To perceive and act. I never hesitated to research design options or ask other developers questions because my ego has never been tied to figuring out the things myself. It's just getting the job done. I'm good at pinpointing key aspects in new environments, processes, or practices, and explaining them to myself and then to others, maybe. So I can also zoom in and out to establish the bigger picture of an overall system architecture or dive into details. Don't put me in a box. I like to tweak software designs, processes, techniques, practices, and then, because I like to communicate, I write papers, essays, and books.
So through comparing and contrasting our Umwelt narratives, we identified a set of threads that cut across our experiences. And we extrapolated these common threads into a set of prompts that people, that's you out there watching this talk, can use to write and reflect on your own software development Umwelt. So we have a bunch of threads, things like origins, which are how we first encountered software and how our interest was nurtured over time, going to work in our first practical experiences, finding proficiency, those are the moments when we first truly felt comfortable creating software, and pivots, which are the unexpected moments when we changed directions. And today we're going to focus on just two of these threads, origins and pivots. And first we're going to share our own experiences, and then we're going to invite you to reflect and share as well.
So we'll start by doing this for the origin threads, where and how we first programmed, and how was our programming Umwelt subsequently nurtured. So I learned machine language programming in the mid-1960s, if you can believe that, at a summer course just before the 9th grade. We programmed the Burroughs 205, a mid-1950s room-sized vacuum tube decimal computer whose main memory was a magnetic drum. In machine language, remember. I found programming to be radically different from other STEM educational experiences. I learned that any information, including CPU commands, could be encoded as groups of numbers. Today, I wonder whether starting with machine code rather than a higher level language was a major factor in shaping how I think about software development. Programming satisfied a creative itch, an inch of an itch. Eventually, software became my creative media. For a couple of years, I didn't have access to real computers, but I immersed myself reading manuals and coding on paper. I didn't need a physical computer to write programs.
Okay, so I had a different beginning. I started out at the university with a part-time job in the test scoring center, where you fill in the with your pencil on a multi-part form. And my job was to ensure that the exams were correctly marked. So I had to make sure that the pencil marks were in there. And then they were read into a machine onto a tape that I had to carry along with a JCL, a card deck, to the computing center to be processed. And the output was a listing of students' test scores and some statistics. And I was like really curious about how that worked. There's a program in there. So I signed up for a Fortran programming class, where it's a Watt 5 programming. So you see the programming manual there. I typed in my programs onto punch cards. They cost 25 cents for 100. And I turned them in and picked up a listing a few hours later. So I got maybe 2 or 3 turns or 4 turns if I stayed late a day. But I discovered that I like writing programs because the amount of effort that I put in paid off in visible results. I could work and work and work and work on my programs as much as I wanted until I got the structure and the logic right, or right enough in my mind. So I ended up with a double major in computer science and cognitive psychology. I started out with psychology and then discovered the computing. So after graduating, I spent 3 months writing thousands of lines of COBOL programs to calculate water and sewage billing for the city of Vancouver, Washington. Fortunately, I shortly went to work after that at Tektronix, which is an engineering company, where I worked in a product engineering culture. I created embedded software and learned that quality and a can-do attitude, just make it work, were what mattered. So getting comfortable with being uncomfortable, as I was in my initial programming classes and in every software project, I've worked on since has led me to expect that you have to find ways to adapt and grow if you want to stretch your abilities.
So I was the child of software engineers, and computers were all around me growing up. So when I was about 8 or so, I remember my parents giving me hypothetical object design problems that I would sketch out by drawing class responsibility collaborator diagrams with pencil on 3x5 note
She was
cards.
good at it.
And I thought these puzzles were fun, mostly because they let me connect with my parents and give me a glimpse into their mysterious work lives. I also went to a summer camp where I created interactive stories using HyperCard, and that was really fun. But then when I was an undergrad, I had to take real programming classes as part of my aerospace engineering degree, and I really didn't like them at all. Programming felt cryptic, something just beyond the edge of my comprehension. And so it wasn't until years later through personal projects and online classes that things finally clicked for me. As a data journalist, I began dabbling with Python and Jupyter notebooks, and that live programming environment was where I actually fell in love with writing code. I really loved being able to tweak a single line of code and then see the results immediately in a data frame or data visualization. I felt like I had agency and power and that I understood what was going on. Yes, there were still moments of extreme frustration, but it felt worth it, right? It felt worth pushing through because I knew what I was working toward. And so I realized that writing software requires a type of thinking that we don't often encounter in other dimensions of our lives, and this makes it both immensely frustrating and immensely rewarding. So as we considered these stories together, we noticed that our earliest memories of making software had profound effects on how we related to it. Alan viewed it as a creative activity. Computers became his muse for his entire life. Rebecca viewed it as a place to problem solve and scratch her intellectual itches. And as for me, after initial frustrations with software development, I was actually inspired to return to it later on because I knew programming was such an important part of my parents' identity. So that really gave me sort of the courage to come back to it.
So another important thread we uncovered as we reflected upon our stories was the major shifts in the direction of our careers in our Umwelt, stimulated by events and experiences. Certain changes in our environment may appear insignificant in the moment. For example, taking a different role for the duration of a project or moving to a development team that follows a different for you practices. However, these changes subtly modify your software Umwelt in ways that open up the possibility of making significant career pivots and seed lifelong interests. Often you recognize these pivots only in hindsight. So in 1978, which was still the early days of the personal computing era, most PCs were still just scaled down mini computers. They were boxes with switches and flashing lights on the front connected to teletypes or alphanumeric terminals. That spring, Rebecca and I attended a talk by Alan Kay titled, "Don't Settle for Anything Less." Kay showed a highlights reel of examples of early Smalltalk and other systems and applications developed at Xerox PARC running on the Alto. The message was clear from the talk's title. Kay's vision aligned with my software design aesthetic, but how could I contribute? I transferred to my employer's advanced development labs, and a couple years later, I had the opportunity to try to make Smalltalk practical for use on affordable personal computers. At first, this seemed like an iffy possibility. Smalltalk was developed running as microcode on personal supercomputers and not on commodity microprocessors. But several false starts later, I was successful. I went on to be the software architect of a family of Smalltalk workstations, and Smalltalk and object-oriented programming became my career focus for the next 20 years.
Okay. So for me, I went from COBOL programmer to software evaluation engineer to software engineer. And after developing embedded software from the ground up, like we wrote the file system, we wrote the operating system, we wrote everything, and then we put our software on top. So I did that for a variety of products for 7 years, and then along came Smalltalk. And to me, it was unlike any programming environment I'd encountered. All right, I was doing assembly language and Pascal, but anyway, it was immersive, it was graphical, it was utterly alien to me. Its syntax was simple, but the terminology they used was really insider jargon, right? So I found that I had to translate Smalltalk terms to roughly equivalent programming constructs familiar to me in other languages before I could even start to understand those guys. And then there was another problem, like what exactly was a Smalltalk application? What were good ways to think about structuring your application? When should I define my own classes, and when should I be using existing ones? I mean, back then it was a zoo. We didn't know what to do. So, so I had to figure this stuff out. And when we make such software, Smalltalk, when we make those pivots to some really radically different environment, we can't simply flush out our existing software development Umwelt and start over. We cannot. We have to live with what we have and move forward. I don't think our brains are wired that way. We can't just go, and there we go. So first I had to transfer the knowledge I already had to this new world, see where my current Umwelt didn't work, and find new ways to think about software development. And so over time, I grew to understand how productive Smalltalkers thought. I was not a productive Smalltalker at first. And I also realized there were different schools of thought about object design. And I found that initially thinking in terms of the roles that object plays and how they interact or collaborate with each other was really a powerful way and the way you did that, if you did that way, you ended up with radically different programs than if you tried other approaches. So this led me to inventing responsibility-driven design, teaching design courses, starting to write books, and I became comfortable with translating what I learned and communicating it to others.
In a previous career, I was a data journalist, and I loved combining data analysis and storytelling. And I was constantly learning new coding and technology tools. Yet I was super frustrated because I worked in public radio. But I made data visualizations and telling people, hey, go follow up and open up this link on a website once you get home, like that does not really work. So I made it my mission to try to figure out how to get more data onto the radio, which is how I found something called data sonification, which are charts for your ears. And I dabbled a little at the time, but then I moved on with my life and forgot about it. And throughout this period of my life, as I was doing all these cool data storytelling projects, things like making stop motion animations about the power grid, something kept me up at night. Our team of reporters spent so much time researching and reporting and communicating stories, but we spent almost no time understanding our audiences. What did they care about? And were they understanding the complex energy topics that we were trying to explain to them? So because of that question, I left journalism to pursue a PhD in information science with a human-computer interaction emphasis, so that I could understand people and how they engage with information and technology. And there, I returned to sonification. But I did so with a new perspective, one that looks at people and technology together as a complex system. So I didn't just think about how to turn data into sounds, right? How to code the bleeps and bloops by writing software. I was also thinking about how people perceive those sounds as well. So when these pivots were happening, we really didn't know just how pivotal they were until we looked back and reflected. By writing our software Umwelts, we noticed how as we pivoted our careers and pivoted the types of software problems we were focusing on, our Umwelts, our ways of thinking about software, changed along with us. Alan found a focus on making software for people, emphasizing liveliness and approachability. Rebecca found a knack for translating existing problems to new ones and using that as a communication superpower. And I developed a sensibility for socio-technical systems, thinking about how people and technology are always intertwined. So now that you've heard us reflecting on some of our formative experiences that have created our personal software Umwelts,
please
we'd
don't
like to
leave.
invite you to do some reflecting on your own. Yes, this is the audience participation portion of this talk. So what we'd like you to do is pick one of these two prompts, either about your origin stories or your pivots, and spend a few minutes thinking and writing about your own experiences. And we've given you some specific questions to reflect on as you do this writing. So after doing that for about 5 minutes, we'll give you a chance to share and discuss what you wrote with the person sitting next to you. And for the folks who are watching remotely on Discord, you can share your notes and thoughts in the Discord chat, and I'll be monitoring those. Ready? So we're first going to spend about 5 minutes thinking and writing. So let's do it, and I trust that Alan and Rebecca will be there walking around the room in case there are
making
questions.
sure people don't leave.
Like
yeah, do stay.
Yeah.
It's time to think about your, either pick origins and nurturing or your pivots, and open up your laptop or type into your phone or do some writing about that. So it's this quiet time, writing time, thinking time. Huh? Oh, in Discord?
It's in the essays channel, and then you have software.
I believe there is a Splash Onward Essays channel, chat.
But you can write on paper, or you can type into your computer, or write on your hand. Yeah.
Yeah, so you can type your reflections into our Discovering Your Software Umwelt Q&A channel on Discord.
Okay, that's good, that's fine. Yeah, make some notes, highlights. I mean,
And with
writing is
questions,
a long thing.
Yeah, like how was writing code different from other things you did?
If you're thinking about origins, your beginnings.
Why did you keep writing code? Why didn't you just give this up?
Most people here probably kept it. You don't. That was very clear from what you built, which is actually pretty cool. Abstractions.
How did you count
yeah,
parentheses?
anyway. How did you pivot to that, though?
How did you count parentheses?
You should write about that.
See? We're about halfway through the torture session here, so.
And some people are talking to each other to pull out their thoughts, and that's okay,
That's good.
too.
That's
yeah.
good.
What was your first programming experience?
So I taught myself BASIC from paper books that I got from a library. So
Okay.
there was no internet. It existed, but it wasn't in my house. So I had this book called Basic Computer Games. So then I would just, and I wanted games, but then of course we didn't have games. My parents weren't into computing. So I just copied the BASIC from the paper.
And it did.
How many tons did your first computer weigh?
Trying and exploring and figuring out, but after a while, then I had a game. It was like a Frogger game, like a little. It had to cross roads, and it would be.
No, the 1130 well.
By cars and trucks.
Okay.
And rat splatter.
So it could do stuff.
It could do stuff. Yes.
I think that was, for me, that common, like, oh, how do you get statistics
About a minute,
out
and
of
then we'll,
these, whatever.
And it was just like it was like playing with Legos, but then this unlimited box of toys, right? And
Yeah.
I thought, okay, if I can make something, then I can
make anything. And
Right. Oh, you were confident then. How old were you?
10.
Yeah, sure. That's like Jordan. Yeah, yeah.
Yeah, it was a bit similar. But I think that was very motivating. And also then, like the games I could make as a 12-year-old were somewhat at the same level as the games that were circling on the diskette.
And you felt pretty good. Yeah. Yeah.
Now it would be really hard for kids to make something that is a game, right?
Yes.
But then the games, the other games that existed were also like a gorilla throwing a banana.
Sure, yeah.
Buildings. So it was like, oh, I think I will enjoy this.
Yeah. So it was like making it do something.
Yeah. But I think it's interesting that your question is, how is writing code different?
Okay,
And
well
for
that's
me it was much more simple.
that's 5
Also
minutes.
like drawing, I also like knitting because
So
I like
the
to make
official program here is to share your thoughts with your neighbors, but I think you've been doing a lot of sharing as you've gone through here. I've been hearing that. So I think we probably just go right into it. Anybody want to share anything they thought about?
Any interesting insights? Yeah.
There's the microphone over there.
Yeah, go ahead, Dad.
Okay.
I actually wrote my first program, multiple programs, in notebooks, multiple languages, without any access to a computer. So, because early age, I just enjoyed the idea of programming languages. I took a programming language course in, I think, 1975 when I was 13, just before going into high school, where I actually was able to finally program in HPL. So technically that was my first language. I then did a lot of programming in high school, and I got a CS degree, but I never took another programming course. So my experience has been with a lot of programming, and I've learned to love programming languages as a means to an end, but a lot of people sort of think in their first programming language, but since I started out looking at programming language before I actually started programming, I sort of
You were a polyglot to start. Huh?
yeah, for programming, and I think it really has influenced, like when I started actually having some work to do to actually do programming and get paid for it, I didn't just sit down and write in the programming language. I remember spending a lot of time with a yellow notepad writing data structures first.
Cool.
And then going to, well, what programming language I'm going to use. So it's a different experience, I think, than a lot of people, especially these days, have, where they get a personal computer or something, and then that's the language, or it's Python.
Yeah. Okay. Anybody else want to share anything? Yeah.
Yeah.
Yeah, must have been, I don't know, 82 ZX81 Basic in the attic of my parents' house. Computer plugged into the television. I'm going to be really sad again. So
sad. Oh no.
So the picture on my phone, which now of course I can't actually show anybody, is supposed to be the cover of the ZX81 manual. It just hates me. It's that sort of day.
Okay.
And the reason is because there was something written on about page 4 of the manual, which says, no matter what you type into this computer, you cannot harm it. Unplug it, plug it in again. Software cannot break this. You can always unplug it. It was so cheap, it didn't have an on-off switch or a reset button, but you pulled the power adapter out, plugged it in again. It said, whatever you do in software, you can always do that. And that was one of the most freeing things, because whatever mistakes I made, pull the plug out, plug it back in again, back to square one.
Well, so that was interesting from my, reacting to what you said, James. It's like the reason why I didn't go into math, because you got graded on the proofs that you could do in real time in exams, right? And programming, you could tweak it. And I went, wow, I can, as much effort as I put in, I'll get something out, which is a similar kind of feeling.
Anybody else want to?
Yeah, Joe.
Well, I don't really want to share exactly what Mary and I had some very good discussions with some things, but I actually had a question for you. First of all, thank you for the very interesting talk, Wurzbach, and Wurzbach, okay? And it's good to see you again, Jordan. You might remember me. I'm Joe with the patterns plot Paris that you did, and thank you for joining during the pandemic. So it's good to see you again. there. But the Umwelt, you got me thinking a lot about that. And Jordan, you said something early on about with the pair programming type things with that. And so one of the things I was realizing that some of these shared types of things going on and trying to understand other people is even some of the experience I've had with swarming or mobbing or things like that. And I'm wondering, because this is kind of a nice little exercise to kind of get a better feel, which I started to with just a little bit with Mary. But sometimes it feels like even some of the pairing, even with, like when I've written stuff with Rebecca or with other authors, and then getting guidance from people like Richard or things like that. But even with software development, sometimes I start getting a different feel of how how people come from that. And so I'm wondering how you think about some of that, or if you have some perspectives from that, from the Umwelt type aspect.
So, go ahead.
I was just going to say, well, you should probably read the essay.
Yeah.
Because in the essay, we're actually
I haven't read the essay
able to do quite a bit more sort of discussion and analysis of various things about that.
Yeah, so I wanted to say something that we started out, this is like Lou inspired us, how did we get our paper started? We wanted to have a paper with Wursprach, and Wursprach on it. So
what's the overlap of the areas we work in?
And then we thought, okay, you know, we don't really understand each other, but we're all kind of doing different things in the software world. And I had been kind of like going off into Umwelts and into heuristics in different ways, and so I kind of brought this idea back, and we just started writing and rehashing till we came up with these various aspects of our stories and how they wove through. So it was like the essay was the end goal. We didn't know what it would be, and this is kind of how it happened. But as we did this, we realized that the real problem, and I have had this problem my whole career, is communicating with someone when you project what you think they are perceiving can cause so many problems in design and in programming. You realize that if someone thinks in state machines, that's okay. You know, that's okay, it's not evil. But anyway, so, but we really need to, and I'd like to, you know, Jordan and I want to take this and have some ethnographic studies and have people share their stories and come to us and do that, and it's not going to be quantitative, it'll be qualitative work, you know. Yeah, okay. So anyway, that's sort of our intent.
Yeah. You could imagine a world where we all have our little card in our pocket, which is our paragraph Umwelt summary, and we meet somebody, go to work with them, you share your Umwelts and say, okay, I get what you're about. And
so anyway, what I'd like to end with, you know, just this part of it is to, if you read the paper, use the prompts as a starting point, modify them to fit your context. Maybe do it with a group of people that you work with, that you want to get to know better. And even if you've worked with them 10 years, you still can always get to know them better. I think that starting with memorable events, so that's why the origin stories were, you know, interesting. Read what you've written and reflect. I think writing, as opposed to just talking, is important. It's hard to do this right for 5 minutes. It's like nobody. Anyway, do this with a buddy or two. Build a reflective community of people you trust. It's not done. So we did this story, and we did this narratives, and we talked about it, and it's like we realized as people in our little buddy system asked questions that we refined what we really were thinking about, what we really meant. I think you can do this and step back. I've already talked to some people who want to try to do this with their teams to see now, how can we, gee, this is interesting. I think that alternating between different modes of doing this, talking, writing, discussing, reading, and if you do this, boy, please share them with us. We can't wait to hear your stories.
Umwelt at Wursprach.com.
We have it, yeah. We have that. Okay.
So yes, I think our time is up. I don't know if anyone's going to kick us out if anyone wants to ask any more questions, but
anyway. Yep.
but I don't want to close down the discussion. So what I suggest is hanging around is always encouraged. So let's thank our speakers again, and anyone who wants to hang around and discuss more, please feel free.
So have a deadline, have a paper, create it.